Alright. Hello everyone. Oh, let me see. Yes, okay. Perfect. I'm gonna put the camera here so I can see you guys. I feel this is better for me because here I have the chat, so it's easier to see. I hope everyone is doing well. Hello and welcome back. So yes, some of you may notice that it's a change of scenery. That's because I'm back at the house where I, live for college. So college is about to start. It starts around like August 31st for me. So yeah, we'll see. And hello Penguin Operator, hello the Ferrari. And yeah, today it's gonna be once again a normal stream. So previous stream we were looking at public key encryption. Today we're gonna be looking at RSA, and then we're gonna learn some more Rust. As usual, the first part of the stream is like some may consider it like a little bit boring because it's just reading a bunch of stuff and trying to really understand it like well. So feel free to tune in and out of the stream. But yeah, it's gonna be our plan for today. I hope to be a little bit more consistent with the streams now that I'm here, sort of get the discipline that originally started all of this. And that's all. Yay. So let's go to the coding scene. I had a Twitch open because I was curious. But let me go here to our City Joy of Cryptography. And let's start reading, I suppose. Okay. So yeah, tune out or something like that. I want this to be part of the process to show that, like, it's not just coding. Like, we also have to learn, we also have to process the information, we really want to understand, and that is part of the learning process. So, yeah, that's all. So, let's begin. Chapter 15, Public Key Cryptography, RSA. In 1978, Rivest, Shamir, and Adelman introduced some of the first techniques for public key cryptography based on the computational difficulty of factoring large numbers. There is no known efficient algorithm for factoring huge numbers, at least not on classical computers. Along with the DP-Hellman-based techniques that we have already seen, RSA techniques are some of the most commonly used throughout cryptography. We have 15.1 Arithmetic Modulo A Composite. Earlier in section 3.4, we discussed the idea of multiplicative inverses. We say that x is a multiplicative inverse of a mod n if ax is equal to 1 modulo n. We also saw that when n is prime, all numbers in here have a multiplicative inverse mod n. When n is not prime, not all numbers have multiplicative inverses mod n, but there is an easy way to characterize the numbers that do. So remember, the GCD, the greatest common divisor, denotes this for a review. Yeah. Theorem. A has a multiplicative inverse mod n if and only if the GCD of A and n is 1. When it is 1, we say that A and n are relatively prime. Okay? Co-prime is also another word. The proof of this theorem uses a factorial number theory called Bezout's theorem. Bezout's lemma actually is the number I've heard it with, but that's okay, which we will not prove. Okay. For all integers a, b, there exist integers st called Bezout's coefficients such that this is true. Furthermore, GCD of a comma b is the smallest positive integer that can be written as a linear combination of a and b with integer coefficients. Perfect. Yeah, this is the usual Bezout's lemma. So let's take a look at the proof. Here we have, okay, suppose A has a multiplicative inverse x mod n, then ax is equivalent to 1, or in other words, ax minus 1 is a multiple of n. Yes, just pass the 1 to the other side, but of course, like, then it's going to be equivalent to 0 mod n, which means it's a multiple. Take case such that this is true. Yes, okay, so we convert the modulo to an actual equality, and then we rearrange to obtain this. Okay, yeah. Since we can write 1 as an integer linear combination of a and n, by Bezout's theorem, we must have that their GCD has to be 1. because it's the smallest, yeah, the smallest positive integer that can be written as a linear combination. And there is no such thing as a smaller positive integer than 1. GCD must be 1. Then suppose that GCD of a comma n is equal to 1, then by Bezout's theorem we can write SA plus Tn to be equal to 1. Reducing this equation mod n gives you this. So 1 is equal to these guys. Let's see. Yes. This is equivalent mod n to something like this. Yes, and mod n is 0, so then you get that SA is equal to 1, and then, yeah, and then you're fine. Okay, this is the Bezout coefficient S is a multiplicative inverse of A mod n. Yeah. So you just discovered an inverse because you found something that multiplied by A gives you 1. Commutativity is not an issue, so applies. Perfect. I imagine like, I guess. Well, this wouldn't be a proof, what I'm about to say. It would be a justification for why, if you are if you share a factor with n, you cannot have an inverse. Which is not to prove what it's being said here, right? Because if you share a factor with n, right? Let's try and think through this. If say you're, right, say you're big A, right? And then you share some sort of factor k with n. So say that n is equal to something else, right, z times the same factor, k. Then big A, right, could just be multiplied by okay, I'm trying to think. Yes, big A could just be multiplied by z, right? Z. This thing would become n. Yeah, and thus this would be equivalent to 0. Right? The problem is z is smaller than n, so it is not 0, it is not n, which means that z is the 0 divisor together with a, and 0 divisors cannot have inverses in a ring. Okay, that would sort of make sense, right? Because if you were to have an inverse, then you would be able to say something like, oh, despite a being a 0 divisor, you can multiply this by, say, if it had an inverse, right, a inverse. Then you get 1 on this side, and z, we already established that this is equal to 0, and then this is equal to 0, which means that z is equal to 0, but, yeah, but z was not 0 from the beginning. Okay, yeah, contradiction. Okay, sure. Let's see. Yeah, I'll be back. Okay, I'm gonna operator. Bye-bye. But yeah, once again, this is the boring part where we sort of, well, it's unfair to call it boring, right? But it is a little bit boring in that, like, we have to read all of the stuff. Oh, shoot, you guys cannot even see very well. Give me a second. Hello, gonna come out. Hello. So, hypermon CFG. I need to change the resolution of this guy. I want a Twitch profile, and I want to apply. There you go. And then I want to set up my monitor so that it's limited. Oh shoot, wait. Apply. Wait. Profiles, Twitch. Apply. There you go. And now I change my monitor. I say enter. Yes, I want that. And here I change my monitor so that it shows me a good ratio. There you go. Okay, now you guys can actually see the thing. So now I can close this. There you go. There you go. Now you can see the text section. So, hi again, Kamal. So, guys, we're currently reading about RSA. We're trying to learn the basics of RSA. We're working with arithmetic, modular or composite, I imagine here, because then this wouldn't really make sense. Everything is co-prime to a prime. So, anyways, all right. Fambiek, hello. I have been coding today too. Yo, let's go. Yeah. So this is the daily dosage of reading instead of coding. So we'll see. So we have here an example. Also, why have you been coding? How is your interface, like the GUI that you were creating, sort of going with Vulkan, if I remember correctly. But yeah, which numbers have multiplicative inverses mod 15? They're the numbers from da-da-da-da that have no factor in common with 15. This makes sense, right? Because their GCD is 1 with it. Which numbers have multiplicative inverses mod 16? All of the numbers that have no factor in common with 16, which would be odd numbers. And of course, right, I'm not entirely sure what I was coding. Let me ask. Alright. Valid. When n is prime, every number is relatively prime to n. Yeah, so this makes sense. Okay, computing inverses. Let's see. Suppose you want to compute the multiplicative inverse of a mod n. You'll probably first compute the GCD of an to ensure that the inverse of a indeed exists. GCDs can be computed using Euclid's algorithm, but making a small modification to this algorithm, we can also compute the corresponding Bezout's coefficients, and hence the multiplicative inverse along the way. I enlisted on one of my old abandoned projects to do bug fixing. Oh, let's go. So the reason why we want the Bezout coefficient is because if we know that the GCD is 1, we're guaranteed that the inverse, or an inverse is going to be present as a Bezout coefficient. So if we modify the GCD algorithm to also extract the Bezout coefficients, then we get an inverse. Perfect. All right, let's see. Euclid's algorithm is GCD. Okay, this is the usual Euclid's algorithm, right? The GCD between x and y is if y is equal to 0, then return x. Else return, well, GCD between y and x mod y. Yeah, and this is the usual Euclid's algorithm. I want to see the extension. Let's see. The extension is if y is equal to 0, then we return x, 1, and 0. So what are their positions? Oh, DST such that the GCD is D and Sx plus Ty. Yeah, okay, that makes sense. If y is 0, then the GCD has to be, the greatest common divisor can just be x. Sure. Else, DST, right, is through the extended GCD. Oh, we just apply the same process and we return D, okay, T, which would be, the coefficient you extracted. Okay, so from flipping the orders, S minus T, and then the floor of x over y. Okay, I think we're gonna get a better explanation here. It was riddled with bugs thanks to my spaghetti code. Oh wait, I think letting it die would be a shame, but it also lost the motivation to keep working on it. Yeah, that happens. Claude definitely has not fixed all of the bugs even after 6 hours, but it's fixed some. Oh, hopefully it'll be able to fix the rest. But yeah, let's see. To compute the multiplicative inverse of A mod n, first run DST with the extended GCD. If D is equal to 1, then S is the multiplicative inverse of A, otherwise A has no multiplicative inverse. And yeah, this we saw before. So we see it in Sage, right? Perfect, implements the extended Euclidean algorithm as X GCD. Great. Algebraic properties. So previously, we defined multiplicative groups for prime moduli n. We now extend the definition to composite moduli as well. Yeah, the multiplicative group mod n called z star n is defined as this, right? All of the things that have an inverse. Yeah, the Euler totient of n, written as this, is defined by the cardinality of z star n. Equivalently, the order of the multiplicative group, right? So phi is the Greek letter phi, or phi, however you want to pronounce it. Yeah, Euler's totient function, the usual. It is convenient to have formulas for phi of n for different kinds of n. It is easy to see that when n is prime, then phi of n is equal to n minus 1. Then you have the p squared, something like p squared minus p, something similar if I remember correctly. And then the general function, if I remember, was n multiplied by the inverses of the prime factors. I did something similar without repetitions. Let's see. RSA based cryptography uses n, which is the product of two distinct primes. Okay, interesting. So the formula for the totient function of PQ is P minus 1, Q minus 1, right? Which makes sense, right? You're able to form things that are not, that share no factor with this number by picking, the P minus 1 that don't share a factor with P, and yeah, it seems to make sense. Let n be equal to PQ and imagine constructing Zn star by first writing down all of these guys, and then crossing out all the elements that share a common factor with n. These are precisely the multiples of P and multiples of Q. Yeah. So these guys and then these guys. It looks like there are P plus Q numbers to cross out. However, 0 appears on both lists, so it's double counted. No other item appears on both lists because the least common multiple of P and Q is PQ, since P and Q are relatively prime. Overall, we start with n equals PQ elements and cross out P plus Q minus 1 of them, leaving us with this. Perfect. You might wonder about the significance of the totient function. Why is it so important to know the number of elements in Z star n? The answer is the following useful theorem you should have called Euler's theorem. Yeah, so that would narrow things down, which we will not prove here. So if x is an element of your multiplicative group, then x to the power of the totient function of n is equivalent to 1. Okay, so before reading, how could this be helpful? Okay, no, I mean, it's pretty helpful, right? If you compute the totient function, then it means that x multiplied by x to the power of the totient function minus 1 will give you 1. So x to the power of the totient function minus 1 is your inverse. If you're able to compute the totient function, then you're able to know the inverse of an element. Any element, actually. Okay, pretty interesting. So the RSA function and RSA assumption say this. Another way to think about Euler's theorem is the following. For all x and all positive integers e, yeah, exactly. In other words, if you need to know the value of some expression mod n, you could reduce the numbers that appear in... Oh, whoa. If you need to know the value of some expression mod n, you can reduce numbers that appear in the exponent mod n. Okay, this is different from the conclusion I thought that we're going to extract. But that's totally okay. And this also makes sense, right? This thing has every single order group divides. Well, I guess that's evident because the totient function is the cardinality of the group, and the order of the group is going to be divided by every single subgroup. So it makes sense why we would be able to reduce it like this. Okay, yeah, sure. Proof. The number e is e modulo totient n more than a multiple of totient n. So we can write this, right? Yes, perfect. This is how modulo works, where k is an integer. Then by the usual rules of exponents, we have this. So this guy becomes 1, and then okay, perfect. Euler's theorem motivates the following RSA functions. So RSA, because of the creators, I imagine, Rivest, Shamir, and Adelman. So RSA. And let's take a look at what these functions are. So RSA functions. Let n be the product of two distinct primes, where n is equal to pq. Let E and D satisfy this. So E and D are equivalent, modulo the totient of n, to 1. The RSA functions are the forward direction, which takes x and returns x to the E modulo n, and the reverse direction, y, which is y to the D modulo n. So now, if you multiply the two together, whoa. Okay, why do we need this? Like, you would get the original element back, right? Because this is, I guess that's the claim, right? The RSA functions are inverses. This is very clear why there would be inverses. Either way, let's see. Composing the two RSA functions gives the new function, this guy. If this happens, then we have that this thing modulo the totient function, it's 1. So two functions composed to give the identity function. Yeah. What about the case of x not being in the multiplicative group? In this section introduces a new number theoretic tools that can help prove the claim for such elements as well. You're asked to complete the proof in exercise 15.25. Interesting. Here we have RSA arithmetic. Here's a toy example implemented in Sage. So, okay, I see. So let's guess what RSA is going to be, because it's sort of hinted at in the fact that these functions are given to us. Probably, right? I feel. Because if you know, right, okay, so this is my guess for RSA. Because we've been given, I feel, the important parts. Like, you can already deduce what RSA is going to be. If you're given, right, the primes P and Q, then you know what n is. More importantly, like, if you know n, you don't know much because you don't know what P and Q are. But if you know P and Q, then you can calculate the totient function really easily because it's P minus 1 times Q minus 1. And then you would be able to know, right, you know the totient function, and then you just need to grab some element E that has an inverse. You two agree on it, and that's gonna be the things you encrypt with, right? Like, E is gonna be like your public key, and D is gonna be your private key. So then somebody encrypts this with E by raising it to the power of E, and you decrypt it by having D. I guess it's a good hint that they're called E and D by encryption decryption. No, so I just noticed that, so I guess that would make sense. And it seems reasonable to believe that's how RSA would work. I imagine there has to be something involved with the choice of E, so that it's not completely insecure. Because imagine, I don't know, you just grab like 1, right? Something like that. I've implemented this before and had no idea about E and D. Oh no! Oh, so maybe E and D are actually not necessary? Who knows? But yeah, E and D, they have to satisfy this? So maybe my guess is wrong. Well, we'll have to see. Maybe they're not used as encryption decryption. Although it seems to be, like, it fits perfectly. I mean, the names, they're your keys. Yeah, okay, exactly, yeah. Encryption key, that would be your public key, and then the decryption key, which would be your private one. Okay, perfect. I mean the names, perfect. Great, okay, so let's see RSA arithmetic. Here is a toy example implemented in Sage. These numbers are far too small to offer any reasonable security, so see below. First, we generate 64-bit primes P and Q and compute n and the totient function of n. So we get PQ, we compute n, which is this huge number, and then we just compute the totient function, which is, of course, this guy. Next, we choose exponents E and D. They must be multiplicative inverses mod totient n, so we must ensure they are chosen relatively prime to totient n. Okay. Oh, I guess. Like, um, yeah, that's kind of funny. So you just grab some random guy and just keep trying until you find an actual. Okay, actual guy that has an inverse. Perfect. And so now the way to compute, we have E, and we compute D by computing the inverse of E modulo phi. Finally, we can use an example to check that raising to the power to the E power into the D power inverses. Yes, perfect. So let's see, security and ETH roots. Suppose N, E, and D have the relationship described above. N is the product of two distinct primes, and E, D are multiplicative inverses, mod totient. The main idea behind RSA is that if you know N and E, but not D, then you can efficiently compute the function x and then x to the e. But there's no known efficient method to invert it. Okay, so finding the inverse of your element is not possible. Or like, well, it's not that it's not possible, but like, it's very difficult. Okay, yeah. Let's see, but there's no known efficient method to invert it. So then x going to xe, modulo n, it's easy given n and then e, right? But it's hard given only n, e, but easy given d as well. Okay, so it's difficult to find the inverse, or like, inverse modulo totient of e. Sure, but then I have a question. Because we saw this. Oh, this is modulo n. Okay, perfect. Because what I was going to say is the remark, right, like, actually, give me a second. Okay, yeah, I might just be stupid. Because what I was thinking was, if we have, say we have x here, right? We know that x to the power of totient is equivalent to 1, which means that x times x to totient minus 1 is equal to 1, which means that x to totient minus 1 is the inverse of x. So given any sort of element, if you multiply it by, but this is normal group theory stuff, right? I guess. Okay, yeah, wait. Okay, so this is something I shouldn't be confused by, right? But I am showing the embarrassment out here just so, we don't know everything in life, and I could pretend like I am not confused, but that's gonna lead us nowhere. So we're gonna have to figure this out. So what I'm saying is my confusion is here with RSA, right? We have this guy E, and we're saying, well, finding the inverse of E is difficult, right? Sort of times something, right? Modulo the totient function of n is equal to 1, right? It's difficult to find who this guy is. But, let me think about this. So, suppose you have an element x from any sort of group, right? You grab that element from the group. Then you know that x raised to, the cardinality of the group, of sort of the subgroup generated by x, is going to be equal to 1, right? That means that x to the power of any sort of thing that has the what's the name? This guy as a as a factor, so say q, right? So x to the power of anything that has the order of the group generated by x, the cyclic group generated by x, is going to be equal to 1, right? Because you just do distribution, right? This is the same as x to the power of, you know, the subgroup's order, which is also equivalent. This guy, we already established this 1, so this is 1 to the q, and this is just 1, right? So independent of what happens, if you have something that has that as a factor, then you're cooked. Which means that x to the power of g, right, is equal to 1. Which means, once again, that x times x to the power of g minus 1 is equal to 1. And so we just found an inverse of x. Right? Like, we know the order of the group. Subtracting 1 from it is not difficult. Raising x to the power of that is also not difficult, because, right? And so what I'm saying is, replace this with e, right? I'm having a caveman moment, in the sense of, like, you know, this is really stupid. Like, when I realize why this argument fails, I'm gonna be extremely embarrassed, right? I'm a mathematics student. I finished my math degree. I'm very rusty when it comes to algebra, unfortunately. It is very embarrassing, but there's only one way to learn. So then we have e, right? And then I just multiply by e to the power of totient of n minus 1. And that would be equal to 1. So this guy is d, right? So I guess the argument would be, computing this totient function is very difficult. If that is what RSA relies on, then it makes total sense. Right? Because then the way to obtain the inverse is, if you know the totient function, then you're good to go, right? I guess, okay, no, yeah, it all makes sense, right? So we just justified why RSA is, okay, yeah, sure. Because if you know the primes p and q, computing totient, this is exactly what I said before. I don't know why I'm repeating it. If you know the primes p and q, then computing totient is really easy, because you just do p minus 1 times q minus 1, because of, you know, the formula for the totient. If you only know n, you have absolutely no clue of which primes make it up, and thus you're able to have, you know, a hard time computing the totient. If you know e, it's still a pretty hard time, because you have absolutely no idea about the totient. And then, right, so returning d, which would be this guy, it's like basically impossible, right, if you only have these two pieces of information. If you were given the totient function, then it would be a field day for you, right? Or if you're given one of the primes, or both of the primes for that matter, but, like, you know. So it all makes sense, right? I want to say yes. I'm just trying to make sure. Okay. And yes, yeah. Yeah, pretty much yes. Okay, the Ferrari agrees. Inverses are unique in a group, and so this is the only way to obtain D. Right? Because if you have A times B be equal to 1, and then you have A times C be equal to 1, then it means that you can multiply, you can grab this function above, and then, let's see, you have A times B equal to A times C. You multiply both sides by B, right? Yeah, and then you obtain that like this is 1, this is 1, so B is equal to C. Perfect. So inverses are unique. This is the only way to compute it. That guarantees sort of like, well, it doesn't guarantee it, right? But it gives you some confidence that like the problem of computing the social function is as difficult as finding the inverse. Some confidence, although I don't know, right, if there is like a formal proof to say, yes, this is indeed the only way. Like, this is, right? Because you could find a way in which you get the inverse, but you don't know the exponent. And thus you didn't rely or you didn't interact with the hardness of finding the totient function. Because then you get discrete logarithm problem, right? Okay. So what am I mumbling about? What I'm saying is like, this gives us a direction, right? This tells us that it is difficult to compute the inverse of E through this method, through the method of finding the totient and doing all of this stuff. It doesn't guarantee that finding the inverse of E is going to be difficult though, right? What if, maybe from 100 years from now, we find some sort of theorem that makes it super easy to find? We're like, oh my god, right? That made sense all along, right? So this is not guaranteeing that finding D is difficult. It's saying that like this method, which is a reasonable method, is difficult. Is this the only method to find the inverse? I would say no, unless they provide a proof that there's actually no other method, in which case this would be great. And what I'm saying is, what if, right? Because then somebody else could argue, well, if in the future we had such a theorem, right, that tells us what this inverse is, then we would be able to look at what exponent of E generates this element we found easily, and by looking at its exponent, we are able to compute the totient function. And thus, whatever theorem we find in the future must either challenge the difficulty of the totient function, in which case all of this falls, or it must be as difficult as finding the totient function, right? It's like a random thought you may have. And my response to that would be, well, there is, right? It could be a method that just doesn't really reveal what the exponent of E needs to be in order to find that element. And thus you'd be able to avoid the problem all along. So let's see. I'm not sure how it's mathematically proven, but it's pretty much impossible without brute forcing. Quantum computers can break it though, and small primes can be broken. It's literally just too inconvenient to break. Yes, so I agree about that when it comes to computing the totient function. And I guess that's right. Not sure if it's mathematically proven. So, because that's my problem, right? If it's not mathematically proven, then it means that in like, right, 10 years from now, maybe the hardness of this problem stays. Maybe it's still as difficult to compute the totient function, but we just so happen to find a different method to compute inverses that just, it's a way easier method, right? So something like that, right? I feel it would be something like, imagine I give you this like huge number, right? And then I tell you, all right, multiply by 10, right? If you were like, say, I don't know, a little kid, right? Multiply by 10. And then you start saying, okay, let me add this number to itself once, thrice, now let's do it 4 times, and so on until I complete 10 copies, and then I will know the answer, right? And then all the kids in the kindergarten will say, oh my god, this is such a difficult problem, right? As you can see, you're going to need a lot of computational power because you need to add these numbers 10 times, and for us kids, that's almost impossible, right? And I agree, this method of computing the multiplication by 10 is indeed sort of hard, right? And you could have some sort of, the kids could come up with all sorts of reasons saying, yes, this is a proof that it takes us at least 2 hours to compute this. But then some random kid comes and say, oh, wait, right, we just discovered this sort of arithmetic textbook, a theorem that proves that just by adding a 0, you get the result multiplied by 10. So the hardness of the original approach is still there. Doing it this way is still really bad, and it's still really hard, and it's impossible to break. But you could just find another method to computing the thing you want to compute that just doesn't interact with this method at all. So what I'm saying is, they're arguing that this method of computing an inverse, which is through the totient minus 1 and e to the power of that, is computationally hard. But there is no guarantee that there's just some random other theorem that we're going to discover in the future that allows us to find inverses. Unless they prove it right here. So we're going to take a look at that. Let's see what the justifications are. Let's see, security and ETH roots. So see, there is no known efficient method to invert it. Okay. So this may just be hinting at the fact that we're relying on a similar like Diffie-Hellman assumption. A discrete logarithm is just, because remember when we were reading Diffie-Hellman, right? They just said like, well, we cannot really prove that discrete logarithm is a problem, right? That just can't be solved. It's just that we've tried multiple things. It doesn't seem to work. It seems to be a hard problem, and thus we rely on it. So I think we're going to have to do the same thing here. I don't know. There might be an efficient algorithm for factoring huge numbers, which we don't know yet. Then RSA would fall apart and high rate event. That is true, right? Like one for factoring huge numbers, but I'm saying that like it doesn't even have to be with factor numbers, right? Like it could just be something completely different. But yeah, because I mean, right? If you are able, RSA or NSA. Hello, Jasper. But yeah, maybe Jasper can also answer this questionings we've been having about RSA, in its actual complexity when it comes to security. Both, yeah. Things the NSA doesn't want you to know. now we're using 100% of our brains. Dude, I swear, we found a way to break RSA. No, it's like, yeah, no, but it's good to contemplate, right? Like, it's possible, oh, maybe this is true, maybe, right? So, I don't know. We'll see, right? So sometimes we refer to the act of inverting XZ as computing ETH roots mod n, which, this is the usual name in algebra, sure. Formalizing this intuition starts with specifying how the relevant values n, e, and d are chosen. So k to b is cos below. Okay, you uniformly choose a k over 2-bit prime p, then we uniformly choose a k over 2-bit prime q. Okay, perfect. Then n is going to be equal to these guys. Why are we choosing k over 2-bits? Let's try and guess. I imagine it's just because, right, the multiplication of these two is going to be at most k bits. It's going to be something like that. Hi, Penguin Operator, welcome back. Yeah. And then we compute n, we draw e randomly from z star totient n, and then we just, we compute d. D we define as the inverse of this guy, which we already established why it is easy to compute d. If you have the totient function and you have everything, right? By whatever we were looking at here. We formalize the idea that computing ETH roots mod n is hard using the following definition. Okay. The RSA assumption is that the following two libraries are in the... Okay, we do not like this word. Okay, are we... Okay. Maybe this is just a way to be like, assumption, but it's actually a proof. Let's see. is that the following two libraries are indistinguishable. So what are these libraries? NED, right? You grab it from the RSA keygen procedure. So you just grab those two. You grab some random element Y. You generate the challenge, run, return these guys, and then you check X. Okay. Let's see. RSA check X. Then return Y equivalent modulo n to X to the E. Okay, and then returning false on the other side. So you would only be able to distinguish this, right? It's exponentially difficult to find a case in which it's going to return true. Okay. The value Y is called the RSA challenge, and the two libraries have different behavior only in the event that the adversary calls RSA check with an ETH root of the challenge. If the two libraries are indistinguishable, then no efficient adversary can compute ETH roots with better than negligible probability, given only the information available to it. Okay, so this is an assumption. It seems to me that this is just another Diffie-Hellman move, right? Or we're just saying, like, we've tried a couple of times, we've seen that it's pretty difficult. Seems like this is the case. We don't have a formal proof for it, but it's pretty hard. So let's see. Jasper has an answer for us. By the way, there are proofs for RSA security except for the fact that factoring a large number into two large primes is impossible in reasonable compute time. That's the intuition. Oh, no proofs. Okay, yes. Okay. So this sort of backs up our skepticism that we had before. Okay, so this is a vibes-based, well, not vibes-based. Because there is, like, there is a high degree of confidence that it is indeed difficult. But we don't have the specific, like, RSA is based on an assumption. Okay, so same as Diffie-Hellman. Yeah, that's what was sort of bugging me out, right? We have no mathematical proof or backing that it's actually true. Okay. Sure. Oh. This is not very okay, well, I guess a good question would be like, are there any methods or alternatives that are actually, there is a proof for their hardness? Which I guess it's also not... I guess it's impossible, right? Well, not impossible because, okay, now that I think about it, right? Imagine you had a cryptography scheme that was sort of that had a proof for the hardness of the problem that is involved in the scheme, right? That says this thing is, I don't know, it runs in exponential time, yes or yes. Like the only way to discover an answer is for it to take exponential time. Then it would mean that the decryption process, okay, hear me out on this. So if you have a method, right? Let me know, Jasper or whoever, if this is not the right reasoning, right? If you have a method M, right, that is computationally hard, that is, it takes exponential time or non-polynomial time, and you're able to prove that, it's proven that this method has to take, like, to discover this thing, it takes exponential time, right? If you have such a thing, then you can form the following scheme. You have M, the method that is provably non-polynomial, and the mere fact that you're able to decrypt things would imply that there's a way to verify the answer to that problem, right? Because if you're able to decrypt, it means that you're able to say, yes, this answer to the problem is correct. A cryptography scheme requires decryption to at least be polynomial, or else it wouldn't make sense, right? And then, if that happens to be the case, then you have a verifier that runs in polynomial time. So it is a problem for which you can verify in polynomial time its answer. And thus you would be proving P equals NP. Right? Am I tripping? or is this like an actual reasoning, right? Because by implementing a completely sort of, bulletproof, this method is unbreakable, it takes exponential time no matter what you do, cryptography scheme, that then takes polynomial time to decrypt, you create a polynomial time verifier for a given problem that's supposed to be, right, non-polynomial, and thus you have broken PNP, and so P is different from NP. Like, if you were able to grab such a cryptographic scheme, you just prove that P is different from NP. Right? And I'm not talking about, like, RSA. I'm talking about, like, a general cryptography theorem in a sense, right? Let's see. So, there are probability tests that are decent. I mean, like Fermat's probability tests. Okay, but none are good enough when considered big numbers. Only way is quantum with Shaw's. Okay. Every crypto algorithm might be attackable by some polynomial time mathematical method. It is all based on current knowledge, except OTP maybe. That might be the only provable secure thing. Jasper says, factoring is believed hard because no polynomial time classic algorithm is known, and several related problems have been studied in depth. Yeah, I imagine, right? There is a lot of backing behind why factoring is hard, but there is no mathematical proof for it. But, it's like comfort at night, I suppose. Jasper saying, factoring is in NP and co-NP-ish territory, but it's not known to be NP complete. Sure. The best general classic algorithms are still sub-exponential, not polynomial time, yeah. The strongest practical hardness evidence comes from the failure of decades of attacks plus links to cryptography, not from a proof that factoring is impossible to do efficiently. Yes, for sure, like, completely agree, right? I just wanted to know, right, because there is this sort of sense in which, right, like, the reason why we prove all of these things is precisely because we want to have like 100% certainty. It's just a little bit annoying that we don't have that for RSA. What I feel what Jasper's saying, right, it's good enough in the sense that, like, practically speaking, do we really need a proof where, 50 years, 60 years, or the RSA paper came out when? 1978. Okay, perfect. So around like 50 years, right, of attacks have proven that RSA has not been able to be breaked, right? Like broken. Except for like Shor's algorithm and all of that, but then, that sort of goes out the realms of classical computing in the first place, so it's kind of like a, like, I don't know, it's like you're playing chess, right? And like this guy says like, oh, you didn't expect this super move, and then just grabs his hand and throws out all the pieces. Like, we're no longer playing under the rules of chess. So I guess, of course, you're going to be able to beat it. But yeah, you can check the word around Pollard's row and Pollard P-1 methods, quadratic sieve, and GNFS. Okay, what are these related to? Are these related to... Yeah, like, why do you think these are interesting? So, and then we can write them down. Because I don't want to write, like, Pollard's row, Pollard P-1, and then I'm gonna be like, oh yeah, like I don't know what we're looking at. Factoring integers, large integers. Oh, okay. That one makes a lot of sense. Perfect. I think, let me write it down here on my little book. But yeah, I do still have the doubt of whether or not, like, the reasoning we just exposed a few minutes ago shows that, like, there is, like, having a cryptographically secure scheme, like, well, not cryptographically secure, but like a provable cryptographically secure scheme in this sense of, like, there is no way to break it unless you perform exponential computation, is equivalent to solving P equals NP. It seems to me like it is. but may be completely wrong. Let me get my book. Let's see. This is Pollard's row. Pollard's row. Pollard P-1 quadratic sleeve. I feel like I've heard that name before, the quadratic sleeve. I have no idea though. Sleeve, and then GNFS. Okay. So things we need to look at. All right. But yeah, if anybody has maybe a rebuttal, some sort of reason why this wouldn't show that, a completely 100% cryptographically secure scheme implies an answer of P is different from NP, let me know. It seems to me like it is. Like I would deduce, but who knows? If you want to look at some C code implementing some of these methods, check the GMP library. I'm gonna write it down. I don't want to look at the C code. I imagine. Oh, okay. Wait. If you mean methods, as in like the Pollard's row and etc., those would be interesting. I don't want to look at a code like implementing the cryptographic algorithms, because that's what we're gonna implement. So I don't want to bias myself on it, but the GMP library, GMP, like GIMP library. All right. I meant the Pollard stuff. Yeah. Okay. That's good. That's good. Close this. Close that. Okay. It's a constant race between cryptographers trying to make crypto algorithms as secure as possible and crypto analyzers trying to find the key in reasonable time. Yeah. Okay. Let's see. So we have the RSA assumption. Where were we? Here we were, right? Security. Yeah, the RSA assumption. So what is the connection between RSA and factoring? I think we sort of deduced what this was, right? If it knows the tertiary function, then it can compute the multiplicative inverse. Yeah, then it can compute the ETH roots mono. Perfect. Thus, factoring n is the most natural approach to breaking the RSA assumption. If factoring is easy, then breaking RSA is easy too. To date, there is no known polynomial time factoring algorithm, at least not in classical computers. See section 20.1. Right, so we have that, like a problem. Cryptanalysis codes the math as well as the implementation. We generally try to break the math first, but breaking an implementation is easy. I remember there was the I forget the name of the company, but they had the hardware crypto wallets. Ended up using Python pseudo-random generation instead of their own, and then it got just completely obliterated. Just not a fun thing, right? Many people lost a lot of their money, but it's it's usual human error, I imagine, that ends up breaking any cryptographic scheme before you're even able to break the math. But yeah, how big should n be? Ooh, that's a great question. The best known method to break the RSA assumption is the obvious one: simply factor the modulus. The best known factoring algorithms are not polynomial time, but still considerably faster than brute force. The following table shows, for a given target value lambda, how large the modulus must be so that these factoring algorithms require 2 to the lambda f. What? This is absolutely insane. What? What? Most of the crypto relies on RNGs, so that's the first thing you need to ensure is fully functional and heavily tested, failing and ensuring proper RNGs and amateur mistake. Yeah, unfortunate for the company, but yeah. Let's see. 15,000. Oh my god. What? The modulus must be 2 to the what? Brother, what is this? It's like 15,000. Well, I guess, like, you know, in the scheme of computers, like, this is not that big. It's not at all big. Because you would need, you know, 15,360 bits. Kind of, like, 61 bits. Which is, like, not that much, right? 15 kilobytes, like, that's nothing. Nothing. It's still, it's like, damn, right? Like, this is a huge number. Wow. Okay. Anecdote. Singapore failed at ensuring proper RNG for the citizen ID cards. So they generated malformed RSA keys that were breakable with a laptop. Oh no! What? Wait, Singapore. Wait, but how? Okay, why? Okay, why were they implementing RSA keys in the ID cards? So, were they like storing them in our database, or was it just like embedded into the ID card so that it would be like very random to get somebody's ID? Let's see, Singapore, RSA scandal. Like, probably I'll find it that way. No. Okay. Singapore, ID. Yeah, ID card, scandal maybe. No, locally. Sensors. Oh no. Wait, what was the name of the article? Sensors use of national identifications numbers. Released a joint statement advising organizations to stop as soon as possible the practice of using Singapore national registration identity card numbers, whether fully or partially, as default passwords or for authenticating the identity of individuals. Oh. I also feel this is, you know, this is kind of a little bit on the company. Like, was it part of the specification that it was, you know, that the IDs were like random? Was it guaranteed? Because, like, if you're just using the ID of a person without even verifying that, like, that's kind of you. Like, but yeah. Okay, let me get Nadia Hanget. Talk. Okay. But yeah, that's crazy. In the meantime, oh, what are you doing? Here's the YouTube link. Let's see. Oh, why am I not able to copy this? Let me copy this. Copy. Paste. Yay. Oh, it's 54 minutes. Okay, it's gonna take. Yeah. So this one you may watch in we may watch in our free time. You guys should take a look at what the Aspercent does. Right, random number generation failures for NT escape, DUHK. She covers the details in the YouTube video. It's a full lecture though. Yeah, we just realized. But can we maybe find like the slides that talk about this and to just like take a look at them? Oh wait, it actually like explains. I imagine if I look for Singapore. Oh, it doesn't appear. Okay. Debian Open SSL, bro. Oh no. Okay, this is really bad. Linux boot time. Failures in low resource advisors, cascading Open SSL. Yes, follow-up study. Juniper. Huawei. Damn. Netscape. The answer in the DUHK attack. This is ANSI. And then this one's, let's see, she doesn't mention it in the slide. She mentions it verbally. Oh, okay. So it's just like a Q&A. Okay, that's pretty cool. But yeah, we'll take a look Animal freedom. Yeah, thank you, Esper. Let's see. It says these recommendations for module size are the same as those for the discrete logarithm problem. Most modern implementations of RSA produce a 32-bit modulus by default. Okay, so it's not necessary to go like as big as this, right? 2 to the 128 is still like an incredibly huge amount of effort required, right? But okay, Singapore's case is just one blunder amongst many. I imagine that's why I was saying like, you know, like we're gonna implement the cryptography library, but please do not use it in your projects because it's gonna be yeah, I don't want to, you know. Random company owner uses like random cryptography library with this random Twitch guy. Like, you know, all of our savings are completely gone. But yeah, anyways. How can you uniformly sample a prime of certain length in an RSA keygen? There is no real shortcut. Sample the bits of a number uniformly at random and test whether it is prime. A famous result from number theory says that O of 1 over k fraction of k-bit numbers are prime. Interesting. Oh, that's that's really unfortunate. Yeah, state-of-the-art primality testing algorithms don't work by searching for a factor of n. Instead, they look for other algebraic properties from number theory to distinguish between primes and composites. These algorithms simply aren't trying to find an explicit factor of n. How exactly should exponents E and D be chosen? So I imagine that. Does this mean that the generation of sort of like, you know, sampling the prime for RSA, or the generation of an RSA, you know, triple is slow? Well, imagine it's slow in the grand scheme of things, but or like not in the grand scheme of things, like slow with respect to other things, but computers are like decently fast at this, right? I guess my only problem would be like, right, if you want to sample, right, if your n is 3072, then your primes are like around, you know, like 1536 bits wide, which is still a lot, right? So 1 over 1536 is like a pretty like a small number. So then you would have to repeat that every time. That's why I suggested you check Pollard's work. Okay. So Pollard's work would be an answer to this. My situation is, we want to continue sort of reading this so that this section doesn't become like very long. Primality testing is how you speed up prime selection. Okay, so that makes sense. I see. So there are just primality testing methods which go beyond like Fermat's little theorem and are actually very fast. Okay, that makes sense. Yeah, thank you, Jasper. That makes sense. If it's easy to test whether a huge number is prime, can't you factor n? And the answer is no, right? Using cathode ray tubes for modular arithmetic? What is this magic? Good at cheeseburgers, welcome back to the chat. Yeah. And then the Kappa guy. Let's go. Let's see. So one good question, right? How should we choose the exponents, right? Yeah, it's brother. Cathode ray tubes. They're the best new thing in the cryptography world. But yeah, how exactly should exponents E and D be chosen? Right? Besides the fact that they must be multiplicative inverses mod totient, there are relatively few restrictions. The cost of exponentiation depends on the number of bits in the exponent, so choosing a small exponent will speed up the corresponding exponentiation steps. However, attacks on RSA are possible when D is particularly small, when it is less than n to the 1/4. So small values of D should be avoided. Small values of E are generally safe for RSA KEM, right? Key encapsulation. However, extreme values like 3 have some mild weaknesses. Many implementations of RSA always choose E to be equal to 65,537. Interesting. So, whoa. So we're able to just fix the value of E, right? I mean, I guess we didn't rely on the hunt, right? E is visible, right? But I thought part of choosing E randomly made the problem more difficult. Right? I guess it doesn't matter what E is, right? Because what you really need to know is the totient function, right? But, yeah. CRT is for Chinese remainder theorem. Chinese remainder theorem, let's go! And yeah. So, let's see. Okay, because if you have what I'm sort of pondering is, right, many implementations use this number, right? Of course, depending per implementation, I guess that's where the okay. What I was gonna say is, wouldn't we be a little bit worried about pre-computation attack, right? Where we say, usually people use this number, let's sort of try and pre-compute stuff. I don't think that's an issue because, of course, n changes every time for every single instance of RSA, so you would still need to factor in a bunch of stuff. If people were reusing the primes, then we would have a very big problem, but I guess E doesn't have much of an issue, right? If you choose a small value for the decryption key, then I imagine, well, first of all, brute force, right? I don't know. I imagine, like, this constant, like this number is still pretty big. So it means there is some sort of method, some sort of mathematical proof that shows you, oh, actually, if you're smaller than this, it's easier to compute. But anyways, all right. Building a chem from RSA, which remember is the key encapsulation that we saw last time, where is a procedure that is allowed to return to you both the ciphertext and the plaintext. And just RSA keys. Okay. The RSA assumption gives us a function that anyone can compute, but only someone with the secret information D can invert. Doesn't this sound a lot like PKE? Yes. Can we use RSA for encryption, where encryption is this guy and decryption is its inverse? Yo ho ho. Okay, that's what we predicted. I feel it was pretty easy to see. That's okay. Textbook RSA encryption is defined as follows. Yeah, you grab your message and then you just, yeah, perfect. That makes sense. That makes sense. The Geeko One, welcome back. Hola, Sharif. Looking handsome today, as usual. Thank you. Thank you. You know. Thank you very much. My hair, there's a little bit of, to desire about my hair. I think I'm gonna cut my hair. It's just really long. Thank you for the compliment, though. But yeah, let's see. This section of the book includes some slight abuses of notation, which I hope you will excuse. In textbook RSA, the sets M, plausible plaintext, and C are not fixed parameters of the scheme, but dependent on particular uses modulus n. A completely precise treatment would define syntax and security with respect to MPK and CPK. Does that plaintext ciphertext possible under that particular public key? Okay, I think this is forgivable. We can spare his life, right, this time around. Textbook RSA encryption is not secure. The main reason is quite obvious. It's deterministic. An adversary who has a guess of the plaintext value can check whether the guess is true by re-encrypting it. So never use textbook RSA for encryption. An adversary who has a guess of the plaintext value can check whether that guess is true by re-encrypting it. Really bad. Really bad. Imagine this would be, textbook CPA attack. Or you could just oh no. Okay, let's see. However, and we were this is exactly what we guessed. It's like never use this. Okay. However, there is a simple modification to textbook RSA that results in a secure KEM. Simply hash the plain text under a random oracle. The resulting instruction even achieves CCA security. Wow! Let H be a hash function with lambda output bits, which we will model as a random oracle. RSA KEM is defined as follows. So let's see. We grab a random plain text. Well, not a random plain text, but yeah, you get the point. Yeah. Okay. We encapsulate. Well, it is a random because this is a KEM, right? So like, yeah, like your oracle is just gonna give you the random guy, right? Yeah. Arbitrary. Yeah. Like it's not. Jasper just put in the better words. So encapsulating PK gives you. We choose a random R from Zn. We generate the ciphertext by doing this. Then we make the plain text, okay, be the result of the oracle at R. And then we return these two guys. Okay. And then decaps gives you SK and then C. So, whoa. R is equal to CD. Yes, this makes sense. This is the inverse function. And then we return whatever the oracle has for us. Okay. The receiver checked the hash received versus the computed hash after. Okay, arbitrary context, not random map. The receiver checks the hash received versus the computed hash after decryption. So, after decryption. Okay, I am confused here. I shouldn't be confused, but I am. The receiver checks the hash received versus the computed hash after decryption. You grab your ciphertext by doing the usual procedure, right? Then your plain text is whatever the oracle gives you. So that would be the hash, right, of R. And then you return these two. Then to decapsulate, you grab the ciphertext and the secret key. You compute what R was, and then you check again with the hashing oracle guy. And then, okay, yes, sure, see if the hashes are equal. And then this allows us to have, because like my only, I guess I oh my god, okay. I see where my confusion was. I'm so stupid. So this is a problem of mine. When we talk about the random oracles, right? Remember how the random oracles are supposed to work, some sort of like a map, right? They're like a map, like a hashing map. You know, it is the concept of a hashing function. It's just that for some reason, when I imagine oracle, I imagine like, since it needs to have true randomness, I imagine this sort of being that just has like a little cabinet with all of the stuff, right, that you have stored so far. In this case, we would have stored R, so it would be able to retrieve what R is. And so what I was thinking was like, wait, how would he be able to like check it if he doesn't have access to the drawer? Like I'm just like yeah, that was just like a trip. Like don't even mind me. This makes this makes sense, right? You're just able to compute the hash. You're able to see, are these two things the same? Great. Okay. This is a CCA secure KEM in the random oracle model if the RSA assumption is true. From this claim, it is enough to prove security for a single encryption. We saw that from last chapter. In other words, that these two libraries are indistinguishable. Perfect. All right, proof. The proof contains two important conceptual steps. The first is to follow the usual strategy for proofs. Wait, no, I still have. Okay. I don't want to leave this here if we're being completely sure that I'm understanding what it's saying. H be a hash function with lambda output bits, which we will model as a random oracle. RSA chem is defined as follows. You should try and write a formal proof using proof for this protocol so you can be 100% sure it's valid. I should. It would take us like a while, but it's an interesting exercise. I'm first trying to sort of understand what's going on. Textbook RSA encryption is not secure. The main reason is quite obvious. It's deterministic. An adversary who has a guess of the plaintext value can check whether that guess is true by re-encrypting it. So never use textbook RSA for encryption. Good, right? Understood. However, there is a simple modification to textbook RSA that results in a secure KEM. So KEM, we saw it last time. I want to make sure that I am understanding the thing I am supposed to understand. A KEM here. So KEM, something from which you can generate your keys and your stuff. You cannot choose the plain text. It just provides you the ciphertext and the plain text that you need to send. Let's see. Key encapsulation. Because of hybrid encryption, there is rarely any need to use true PKE for anything. So hybrid encryption, we had it here, right? Much lower than symmetric key cryptography, where you encrypt the keys, send them over, and then you perform symmetric after you've gotten the keys, right? Perfect. Suppose Alice has published her public key PK, and Bob wants to send her a large file. Using PKE directly on a large file would be incredibly expensive. Instead, Bob can do the following. Sample fresh K for a symmetric key encryption scheme. Encrypt K under PK using PKE and send it to Alice. Although PK encryption is slow, we're encrypting only a small value. And then we encrypt a large file under K using SKE and send it to Alice. SKE encryption is fast for this large file. Okay, I guess yesterday I was tired after reading and there were things I didn't question. So we're gonna have to go back to this. I need to question some things here. I know. I run the risk of seeming stupid, but we're learning here. So everybody, time to learn. You use PKE for key exchange or key agreement for running a fastest stream cipher for the remaining exchanges. This makes sense, right? Where you encrypt the key instead, and then you send the key over, and then you run symmetric key, because symmetric key is faster, right? This makes sense. My question is, what is the need to encrypt the key and then send it to the other person if we already have Diffie-Hellman, right? Like these things still need Diffie-Hellman, like PKE, like, right? So that is what is confusing to me. Why are we, it's just another alternative and I use kits for RSA. Okay. Okay, but okay, this doesn't. Okay, so then my question would be like, why? Right? Sure, it is an alternative, but this alternative is used in the real world as opposed to just using Diffie-Hellman. Because for the PK, for the PK scheme, you're still going to use, well, Yeah, I mean, like, encrypting and then sending, right? You could just use Diffie-Hellman, which I assume may be faster. Maybe that's my wrong assumption, that it's Diffie-Hellman is not faster than just... But the argument here is precisely, you know, public key encryption is slow. Is Diffie-Hellman slower? Because if Diffie-Hellman is not slower, then you just, you know, you just send it over. It's faster, it works the same way, you both got the key, and in the end you both ran symmetric encryption. RSA is mainly better for signatures and key exchange simplicity, while Diffie-Hellman is better for shared secret agreement with forward secrecy. Yeah, I agree. Like, I wouldn't be saying about like RSA per se, but like about the concept of KEMs per se, or like hybrid encryption itself. Right? Like, why does the concept of hybrid encryption even make sense? Or like, it makes sense, but like, why use it when you can just like, there's no need to encrypt the key, you just Diffie-Hellman and like achieve the same thing as hybrid encryption. You do it faster, you do it simpler, and everything is the same. So that's what's confusing to me. But for mono-secure key exchange, Diffie-Hellman variants like ECDH are usually preferred because they can provide forward secrecy, and RSA key exchange does not. I see. Sure, but like, there's also the fact that no need for both parties to generate matching parameters the way DH often involves group or parameter choices. I guess so. I guess that's a good response, right? You don't really need to agree on a generator, for example. Yeah, and the usual easier certificate integration in many older PKI setups. Okay. Okay, so KEMs are just like some, you know, we woke up and said, what if we just don't use Diffie-Hellman because I'm feeling angry today? And I mean, of course it's not that, right? I suppose it has its advantages, but it is, everybody's moving away from RSA nowadays. I see. Interesting. Yeah, because then what I was questioning was like, right, if hybrid encryption is like something that's not really worth thinking about, why would we need like KEMs, right? There's rarely any need to use true PKE for anything other than encrypting uniformly sampled values. A key encapsulation mechanism is a specialized PKE that is capable of only that. It can encrypt only pseudo-random plaintexts. In a PKE, we tell the encryption algorithm our choice of plaintext, but in the KEM, we let the encryption algorithm itself choose the plaintext. Although this might seem like a strange modification to make to a PKE, the benefit is that a KEM ciphertext can be shorter than a traditional PKE ciphertext, right? To differentiate KEMs from traditional PKE, we usually refer to the algorithms of a KEM as encapsulation and decapsulation rather than encryption decryption. Perfect. A key encapsulation mechanism, yeah, this is what we saw before, right? Yeah, so this is just the generation of your keys. It gives you the private key, it sends it over, well, sorry, it doesn't send it over, it like sends it over but to you so that you know what the private key generated was. So yeah, so here, to encrypt, so we run RSA keygen, right? We are provided our ciphertext, we are provided our plaintext. So that's going to be encapsulating this guy. And then after that, yeah, where's keygen being ran? Wait, okay, no, I do not see this. Yeah, ECC plus PQC is the way to go. The answer there is pseudo-random plaintext, hence the hash in the previous RSA scheme. Yeah, Goody Cheeseburger says Alice and Bob wants to steal the keys from. That's true. So the KEM, right? There's something. Okay, encapsulates a randomized algorithm that takes only a public key as input and returns both a ciphertext and plaintext. Decaps is the same as in a PKE scheme. It's a deterministic algorithm that takes a private key sk and a ciphertext C as input, and returns a plaintext or raises an error. So the plaintext term is, of course, it's going to be the value you two agree on. Right. Eve is the eavesdropper, Alice and Bob just want party and don't want Eve to barge in. True. But, you know, if there are no keys left for Eve, there's nothing Eve can do. Whoever came up with those names when dealing with encryption. Let's see, wait. Keygen is the same as in a PKE scheme, a randomized algorithm that takes no inputs and outputs a key pair. So this guy generates the key pair, PK and SK. Encapsulating takes the public key and returns a ciphertext and a plaintext. And then decapsulating is the same as a PKE scheme, a deterministic algorithm that takes a private key and a ciphertext as input. Okay, yeah, so the plaintext M is the key that you want to share with the other person. My thing is, like, this doesn't... Okay, I am just stupid. Let's see. A KM is correct if the following process is true. PK and SK, keygen, right? I get these two guys, and then I decaps with my secret key. I want to see sort of the use. Algama, there you go. Is that their ciphertext can be smaller than those of a PKE. Algamal encryption provides a great example. Recall that Algamal ciphertext consists of a pair of group elements that have the form this. The security proof argues that PKR hides the plaintext, because PKR is pseudo-random given PK and G to the R. But if PKR is pseudo-random, why not just consider PKR to be the plaintext and let G to the R alone be the ciphertext? The result is Algamal KEM, and its ciphertext consists of just a single group element. Okay. So yes, Algamal encryption using these elements makes sense. Usual, per Diffie-Hellman type of exchange, sure. Then we do let G be a secret group of order n would generate then Algamal KM is defined by the following. So we generate a secret key. We have our public key, and that's what we return. So this is sort of Alice's side of the deal. Where do encapsulation and decapsulation take place? So encapsulation of the public key is we sample R to be random. Then we make C be okay. Then M is the public key, which is whatever Alice sent us, to the power of R. So that would be our agreed value. I am... G to the R alone be the ciphertext. So, what? We generate the keys, public key and secret key. We encapsulate the public key, which is we grab a random R, we choose our own sort of element. This would be what, like Bob's side of the deal? And then M is the agreed value. Then I return C and M. And then we decapsulate. Yeah, I am so sorry, guys. I'm not understanding why we need KEMs in the first place. Because, like, okay. So this is my confusion. Right? Maybe you guys can help. KEM gives to you the ciphertext and the plaintext. It's not like you're encrypting some value that you decided. It's not like you're transmitting some sort of information that you want to communicate to the other person. No. This generates the plaintext and the ciphertext. So the only way it's reasonable to be used is for the keys, right? It's like, let this guy generate a key for me. It's like the only thing I can see it being used for. Let me know if that's not the case. So the KEM just generates some sort of key for me, which would be the plaintext M, right? My only problem is, like, you already generated the keys through the keygen procedure, right? And, like, for the other person to decap what you send them, they need the secret key. It's like, I just don't understand the purpose of KEMs. I just take some random public key. Let's see. Maybe Jasper has an answer first. KEMs are needed because public key crypto is usually bad at directly encrypting large amounts of data. A KEM lets two parties establish the shared secret securely, and then they use a fast symmetric cipher. Yes, okay, so KEM is used to have sort of a shared secret, right? Something that the two people know, which in this case would be the plaintext M. It is, a value that you don't choose. It's just the value that the procedure, the KEM gives you, but it is a value that will be shared in the end, right? I agree on that. Okay. So I understand that part. My thing is, well, first of all, Diffie-Hellman can be used for that, but I guess that's not part of the argument. The other part is, because Jasper already gave a justification for why that, why we may want alternatives to Diffie-Hellman. The thing is, who runs MCAPs and who runs DCAPs, right? Because for the two to share this sort of secret, right, I would encapsulate the value first and get M. And of course, I'm not going to send M because this is our shared secret, I suppose. So I would just send C. So then I send C to the other person. But then the other person needs the secret key to decrypt whatever was in C. So I also need to send them the secret key, which makes no sense, right? This is what confuses me. The other party needs SK, right? So it's like, right, how or actually, I may just be stupid. Yeah, I may just be stupid. Server generates PK and SK, sends PK to the client, client runs NCAPs with that, sends C, server decrypts C. Yeah. Client has access to public key of server and vice versa, so no need for secrets to travel through it. Yeah, I'm just being stupid. Yeah, thank you, Jasper. Yeah. No, that makes sense. Okay. Yes, perfect. PK is generally available through CA, a certificate of authority. Okay. All right. So that makes sense, right? So this is basically Diffie-Hellman. Okay, I cannot stop glazing Diffie-Hellman, but it just seems to me like we're just solving the same problem over and over again. I understand there are advantages, but like, you know, it's like, okay. And then we have the justification here. Yeah, it takes no plain text argument, right? These parts sort of are very understandable, right? Very, you know, pretty cool, pretty good. Oh, whoa! Infinite Coder 01 is rated with 46. Yo, Infinite Coder! Hello. Hello. Guys, we have to rate people. We have to. Please don't let me forget. Please don't let me forget. But yeah. Yo, hello, people. Let's see. Jasper says, when you connect to Google, their servers share their public key with your browser, and there's CA ensuring that it's really Google's PK. Pretty good. Okay. So, Infinite Rage, and then could you use mkcert to gen this locally to test? It says good cheeseburgers in response to Jasper's comment. Hi, Infinite Coder. Yo. But yeah, okay. So KEMs now make sense to us, right? Depends what you're doing, but for testing, yes, you can self-sign. But yeah, okay, KEMs make sense now. Right? 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 Okay. Yeah, I feel this makes sense. So they have the advantage that the only thing you need to transmit is the ciphertext. Right? Like there is not much else needed. You don't need to agree on a generator for the group, as in Diffie-Hellman. Yeah, so their ciphertext can be smaller than those of a PKE. I agree. Okay. Because another question. Maybe you can say on the other side. I know I'm being very, very persistent and all of that with Diffie-Hellman. I know, but I just want to resolve the doubt. With Diffie-Hellman, the only thing you need is to agree on a generator of the group. Other than that, you transmit the same amount of information as with a KEM, right? Because all you're doing is just first, Alice sends their group element, Bob receives it, and then Bob sends his group element. So that's one exchange, two exchange. With KEM, server generates the keygen, sends PK, client encapsulates PK, sends ciphertext. So it's still two of them. You just have the thing where like you don't need to agree on the group generator. I feel that like sure that's enough to choose KM over Diffie-Hellman, but are there any stronger reasons? I just want to know. When you deploy, you need a CA to not get flagged as suspicious. For Wii servers, you can check Let's Encrypt. They offer a free CA. Interesting. So, I guess there are more. There is sort of the situation. For web server. Okay. For Wii servers. I thought you were classifying yourself as a server. You know, there's like, right. I feel like, in the world of the internet, would you be a server or a client? This is a very interesting question. Sort of like choosing Harry Potter houses. Yeah, I feel everybody would want to be a server. Anyways, I feel I digress. So are there any other better advantages to KEM other than you just don't have to agree on a group element? Which seems to be like a little, I am a server. It depends which dimension you're looking from. I see. Pretty good. No. Clients and servers in the interconnected internet. Just realized this can be just used for a bunch of innuendos. So I'm not going. Okay, KMs are not that great. Almost everyone uses DV element with DCC. Oh, okay. Glad to know this is another DV element W. Okay. But yeah, Joseph E. West. Hello! Welcome to the chat. Welcome to chat for the first time. Yeah. Hope you're having a great day. Yay. Okay, we were with the, with this guy. Now people are moving to PQC, another rabbit hole. We would have to. I just wanna. What does PQC stand for? PQC cryptography. Oh, post-quantum cryptography. Okay, yeah. I imagine it's this. We read about this one in the last stream where we saw the lattice-based constructions, were basically the most popular sort of approach to post-quantum cryptography. But yeah, it's pretty good. Let's see. We have a construction right here. Let H be a function with lambda alpha bits, which we will model as a random oracle. This is defined as follows. So now we just create a KEM through RSA. We generate the keys, right? Public key and private key. We encapsulate them by choosing a random element, make the ciphertext be R to the E, right, modulo n, yes, and then we make the random oracle just give us a random value depending on what R is, and then we just return C and M. Okay. Then decapsulation involves having this guy, and then we return the hash. Okay. So this is okay. It seems to me like a little goofy, in a sense. That like kind of the way we are doing this is saying textbook RSA encryption is not secure because it is deterministic. And so what we're doing is we perform a kind of deterministic computation. We just feed it into an oracle, and then the oracle will give us randomness. Well, I guess it's the reason why we need encapsulation, right? So that you don't choose the plaintext, and the plaintext can just change. Just be chosen randomly. Okay, I see it. Yes, lattices and isogenies, it's another world, I imagine. Yeah. I like what I'm seeing on the screen. Yo, let's go, Joseph. You're interesting too. Yo, let's go. Perfect. By the way, my optimized SHA-256 assembly implementation is orders of magnitude faster than OpenSSL on x86-64 and RS. Oh, really? Brother, what? Yeah. Bro, Jasper is reinventing the world as we know it. Wait, this is crazy. Okay. I guess I guess the VODs are still there if you finished it today. I don't know if you had a stream for it. But I have to see this. To see the process of the thing is like, right, I don't know much of the assembly required and like etc. But hopefully we I would like to take a look after this, because that's crazy. Better times than OpenSSL and Arch64. That's insane. I built something you'll love. Says Joseph to Jasper. Does Libsodium do SHA-256? It's been a while since I had to use it. I'm not sure what Libsodium is. Maybe you guys know what Libsodium is. And I'm going to start that challenge that you inspired me for. The 1 billion notes for the Merkle tree challenge. Let's go! Perfect. That's good. We guys tune in to Jasper's stream for the 1 billion notes Merkle tree challenge. This seems like a Mr. Beast video. Today we read out 1 billion notes for a Merkle tree. Yeah. And yeah. Alright, people. So what are we doing here? We're choosing a random thing, right? We're choosing the random R. We create the ciphertext from whatever we generated in the public key. and n is just considered to be whatever the hash of that is, of r. We return C and M. And to decapsulate, we just grab whatever this hypertext is. Yeah, I don't know. This makes some sense. Nice. Yeah, that's very nice. You'd have to trust me, rather the code. It's more than code. Nobody else has and will never have it. Wait, what specifically? Let's see. Can we see what Joseph is referring to? Oh shoot, I opened the sorry. Can I? Has what? I don't know what Joseph is referring to. Oh, did I pin the message? Are we talking about the fabric of the universe? Okay, wait, I cannot see which message Joseph is referring to. Do you mean like the Merkle trees? Oh, you don't have to trust me rather than the code. It's more than code. Can I trust you with my secrets? Oh, that's the message. Okay, perfect. Fabric of the universe is a code with a lot of nodes, information with billions of lines of math done. Ooh, interesting. We'll see. Maybe you can show it to Jasper. All right. It's my own device. Okay, pretty good. So we have the proof for associated security for RSA. I mean, is it task of firmware? Something within these lines? Ooh. Jasper's trying to guess. Let's see, we have the Chinese remainder theorem. Let's go. Chinese remainder theorem. In RSA-based cryptography, one user knows the factorization of the modulus. This section introduces a technique that allows for faster modular arithmetic, and the factors of the modulus are known. Something to do with quantum physics. What is Joseph doing? Oh my god. Let's see, history. In the Sunzi Suanjing, written sometime around the 4th century CE, the Chinese mathematician Sunzi posed an interesting puzzle involving remainders. We have a number of things, but we do not know exactly how many. If we count them by 3s, we have 2 left over. If we count them by 5s, we have 3 left over. If we count them by 7s, we have 2 left over. How many things are there? Sunzi's puzzle is the first known instance of a system of simultaneous equations involving modular arithmetic. In our notation, he is asking us to solve for x in the following system of congruences. We can solve such systems of equations using what is called, in the West, the Chinese remainder theorem, CRT. Below is one of the simpler formulations of the CRT involving only 2 moduli. Suppose the GCD between P and Q is 1, not necessarily primes, but merely relatively prime. Then for all integers u, v, there is a solution for x in the following system of equations. Furthermore, this solution is unique modulo PQ. Proof. Since GCD is equal to 1, we have by Bezout's lemma, I'm not going to say lemma because that's how I know it, for some integers s and t. If we reduce the equation modulo P, we see that T is the multiplicative inverse of Q mod P. Yes. Now set X to be equal to SVP plus TUQ. Then, modulo P, you have this. Right? TQU is equal to U. So TQ is the inverse of U. So X is equivalent to U modulo P as desired. Okay, yes. Sure. So we're reasoning mod Q shows that X is equivalent to V as well. Thus, X is the desired solution to both equations. So we just use Bezout's lemma, and then we just compute X. Perfect. Now we argue that the solution is unique modulo PQ. Suppose X and X prime are 2 solutions, so we have this. Since X is equivalent to X prime and is that, it must be that X minus X prime is a multiple of P and a multiple of Q. any number that is a multiple of p and of q is also a multiple of the least common multiple, and then it's 1. Okay. Yeah, pq, since p and q are relatively prime, thus this guy's a multiple of pq, so it has to loop around before it even happens. Oh, okay. Perfect. CRT now, using Chinese remainder theorem for modular arithmetic. So before we start, let me read the chat. Let's see. An emulator? I assume that given the prominent numbers of lines mentioned, most of the code is auto-generated, not handwritten. Sort of, lol, but I need to build it. It's more or less me testing theories and proving people right or wrong. It's about bridging gaps and stuff. Yo! Of course scripted, yeah. I won't type billions of lines. The device tests everything out and constantly feeds me data back to observe physical and non-physical data. Then, I briefly worked on optimizing the code for a quantum simulator. What the fuck? That was running DSL generated code. It's mind-bending. I rewrote certain laws myself, just have to test the device. It scares me because it's a high voltage device. Bro, please don't die. Are you trying quantum cells and combining them to build an emulator? Or do you have solid hardware? If set up wrong, there goes me. Oh no. But yeah. Let's see. Another way to think about the Chinese remainder theorem is if you know x mod p, and you also know x mod q, and you can efficiently determine x mod pq. This observation leads to a different approach for doing arithmetic mod pq. Suppose p and q are relatively prime and you want to know the value of some complicated expression mod pq. One method to compute its value is this. Evaluate the expression mod p, evaluate mod q, apply Chinese remainder to these two results to solve for the answer mod pq. Example, addition using CRT. Let's start with a simple example, right? We want to know the value of 3 plus 7 mod 15 to compute it using the CRT recipe. Value of the expression mod 3, that's 1. The expression mod 5 is 0. Use CRT to solve it. We see that the result is 10. This was a little bit of a dumb example, but okay. You can compare the CRT addition recipe to the normal approach with the following sage code. The same recipe works for multiplication too. Let's compute 3 times 7 mod 15. We evaluate the expression mod 3 mod 5, and then use CRT to solve for x that satisfies this guy. The result is 6. Pretty good. Applications to RSA. This is the interesting one. You may have gotten the impression that the CRT recipe for modular arithmetic is convoluted and wasteful. That's true when we're evaluating simple expressions like addition and multiplication as in our examples, but remember, RSA-based cryptography involves modular exponentiations with huge exponents. The CRT method is significantly faster for these exponents. Sage, the usual way to compute an exponentiation like this is this guy. Okay, if we know the factorization n pq of the modulus, we can use the CRT recipe. That is, we can compute x to the modulo p, x to the modulo q, and use CRT to solve for the answer pq. Oh wait, this is interesting, right? It makes it more efficient. Perfect. Both of these methods will compute the same answer, and we can measure them to see which is faster on large inputs. Below is a test from my laptop using a 3072-bit RSA modulo, so P and Q are each 1536 bits. So let's see. Time. 125 loops, best of 3, 617 milliseconds per loop. Wow, it's half. Damn. To understand why the CRT method is faster, it's enough to know that the cost of standard modular exponentiation of a k-bit modulo is O of k3. For simplicity, let's pretend that exponentiation takes exactly k3 steps. With the CRT method, we perform an exponentiation modulo p and another modulo q, but p and q are each only k over 2 bits long, so the overall cost is this. I see. By this rough analysis, it is 4 times faster than the standard method. In reality, there are other costs slowing down the CRT method, which is, this analysis doesn't account for, like the cost of solving for the answer mod pq. Still, the CRT method is indeed noticeably faster in practice. That's pretty interesting. Remember, in order to take advantage of the CRT speedup, you must know P and Q. In RSA KAM, for example, only the private key holder will know this factorization. Thus, Decapsulation can be sped up, but encapsulation cannot. Pretty good. Let's go. We finished chapter 15. Now we know how RSA works. I feel this was one of the more entertaining chapters, in my opinion. Like, I really enjoyed this chapter. Pretty good. Yay! We finished the chapter. Now we transition to the second part of the stream. I need to learn Rust. Yeah. I don't know much about Rust, so we're gonna be learning some Rust, and you're gonna see me struggle with whatever the Rust concepts are. I want to read the chat though before we transition. Let's see. I rewrote search and lost myself. Yes, we saw that. Quantum self. Yeah. I have to build it all from the ground up. I'm doing the math right now only. I have to get the materials and whatever else is needed. Wow. Sounds like an experimental garage-made device, one wrong move and kaboom. The BP right now, it's sort of in testing phases. It is, but it won't blow up. It's lethal shocks I'm worried about. Dude, what? Be careful and make safety a priority. Of course, nothing's worth losing your life over. Ever a quantum, even a quantum computer, yeah. Of course, bro, I'm trying to find a place that can take my project in. Make sure your prototype doesn't vaporize you, though. True. It won't. I am more scared of the voltage, man. Maybe build a robotic arm to connect it together. Yeah. Mode XP is the Achilles heel of RSA and ECC. It's tricky to have it implemented in constant time. Most native implementations leak secrets through timing. Interesting. Yeah, if you haven't started, this is the best intro to Rust. Yeah, wait, no, we have started and we've been, you know, struggling a little. But yeah, is this the Rust book? Yeah, this is the Rust book. So we've been taking a look at some stuff as we go. Wait, no, this is not the Rust book. No, this is the Rust book. Wait, but it's like different. Wait, or am I talking about Rust by example? Oh, I think I was talking about Rust by example. Never mind. Okay. This is the Rust book. This is Rust by example, right? Assume so. Okay. So, my people. By the way, you want to see a cool thing I added? Well, I think you guys cannot see it that well. That's okay. I added this menu selector for the wallpapers. Look, damn. Yo, then I can choose the rocks. The valley. Oh my god. And then the watchtowers. I love the watchtowers. You cannot see the watchtowers because my monitor is like, it's supposed to be a wide monitor, right? It's like a 21:9 ratio, but I like cut it down to 16:9. Anyways, yeah, that's it. That's that. I like the watchtower though. Okay. So now we gotta open Visual Studio Code and pray that the stream doesn't fall down as VS Code consumes all of my RAM. Okay, seems like we're safe. 6,000 is still normal. Are those Firewatch inspired or just normal watchtowers? Those backgrounds just come from like the art that was created for the Firewatch game, if I remember correctly. I think they're made by Olimos. I think so. Joseph is asking the Ferrari, when's the next stream? The Ferrari, you haven't streamed in like a week, brother. The people need you. Yeah. Sorry, I was here editing. I added like a little explanation for our memory allocator. For Nalloc, and you know, hopefully it can illustrate all of the decisions we made. I'm on vacation till Friday. Oh, pretty good. All right, let's open. I think it was rustlings. Let's open rustlings. Yeah, there you go, rustlings. So you're learning about move semantics. And move semantics, I have like a little bit of a little bit of a fear because a lot of people have told me they're really bad. That like it's very difficult to understand move semantics and the borrow checker and all of that. So let's see. All right. So we were in move semantics 1 and then move semantics 2. It says to do. Let's see. I'm gonna hide this. All right. Maybe only one of them. Yeah, I feel that's better. To do. Make both vectors, vec0 and vec1, accessible at the same time to fix the compiler error in the text. So what do? We create a vector, then we create vector 1 by using fillvec. The problem is that fillvec actually just like uses, it like takes ownership of this guy, right? And so, okay. Maybe what we can do is like, instead of this, well, actually, Oh wait, they're different, right? They're different vectors, so never mind. I was gonna use like a mutable reference. Yeah, what did I do? Borrow of values, let's see. So is .clone what I'm supposed to use? The borrow of this moved value. I mean, there is no other way, right? Other than, like, because if you want to have two vectors, you better clone the one you're coming from. I guess, right? But like, is this what they intended me to do? I think so. Next. Let's see, move semantics 3. Alright, dude, let's see, what's the problem here? Fix the compiler error in the function without adding any new line. Oh. Okay, move semantics. We grab vector 0, we grab vector 1, and then we do stuff to vector 1. Then it says, cannot borrow a vec as mutable, as it is not declared as mutable. Cannot borrow as mutable. Wait, so do I just do mute vec or something like that? Oh. Great. Awesome. Move semantics 4. Wait, this is okay, this is going well. I don't want to jinx it, but it's going like decent. Right, which is the great thing. Move semantics 4. Okay, let's see. Don't add, change, or remove any line. What? Oh, by reordering the lines. Okay. So here, let mute x be equal to this guy. Let y be equal to this. Let z be equal to this. Okay. According to the Rust book, you are not allowed to have two mutable references alive at the same time. And so what we need to do is we need to do something like this. Because the... Shoot, I forget the difference between lifetime and scope. It's either lifetime or scope. It's like, I think the scope refers to this entire thing because it's accessible through here. Lifetime is only this guy because it's the last use was generated here. So after this case, this little guy dies. Right? But the scope is the entire thing because I could just happen to reference it after. Right? And then the compiler would be mad at me because now he's alive for more. Yeah, okay. True. Let's see. That's always good to hear. I hope it stays good. Oh, yeah, Ferrari's vacation. Better take a good vacation, Ferrari. But yeah, this language is something else, man. I think I can get into it though. It's really dope. Alright, people, well, we'll see. We'll see what happens. Will we end up hating rusts? Is it gonna be a love story? There's only one way to know. Let's see. Fix the compiler errors without changing anything except adding or removing references. The character ampersand. So this guy shouldn't take ownership, but it's currently doing that. Okay. This guy should take ownership. Okay. Well, what are we doing? So we're grabbing data. Then we get the character data. What is get char? Oh, get the last one. We get the last one and then string uppercase and then we pass in this guy. Okay. So I assume that to get the character, we don't really need ownership. We only need to borrow it. And we don't need to mutate it, so we only need a reference. I should solve one error, which is this. What? Oh, and then what? Wait, does Rust not immediately modify it so that it deduces that it needs to be, what? Okay, so this would be a string reference, right? Rust requires me to specify that what I'm passing is a reference? I see. So this is not like C++ that just like automatically does it. Which is great, by the way. It's great that it's explicit. Then string uppercase, where it says it should take ownership, so I imagine we just remove this guy. And then we just like say goodbye. Damn. We are professionals at Rust. Oh, that was all about move semantics. Great. Okay. Structs. Okay, this is interesting. So we have at the fields that the test regular structs expects. Okay, so we have this guy. It's expecting red, green, and blue for a regular struct. What are the minimum and maximum values for RGB colors? Am I able to specify minimum and maximum? That's kind of crazy. Okay, what types should they have? So RGB is 256, which would be just like I8 or something like that. Well, it would be like unsigned in 8, and then I would just say like red. Oh shoot, is it this way? Unsigned in 8. UI. Hello. I8. Yeah, but I want the unsigned version. I want UI8. Oh, it's just U8. Okay, great. Struct fields are separated by comma. Okay, first wrong decision from Rust. Oh no, they use commas. This is really unfortunate. Blue. I have to admit that like it is strange to write things this way to me. I feel like being used to C++ makes me want these guys to be on this side, but like somebody that has an addiction, right? They're able to recognize that there is a problem and that there is a better solution in it. It is for their well-being that like they should leave their addiction. I feel the same here. I feel this is like a better way to put types in, despite how much I, you know, I like clash cognitively with this. Because then you can align them, and then they look cute. But yeah. Anyways, oh shoot, okay. Color tuple struct. Add the fields that text tuple struct expects. What? What are you expecting? You're expecting 0, 1, and 2. What am I supposed to do? I feel like it's pretty clear. Why are we using parentheses instead of keys? Is that like a gotta be something like parentheses means the compiler is allowed to reorder them. Keys means the compiler is not. I swear it's gonna be something like that. I'm scared. Can I do the same thing? Red U8, comma. Oh shoot. Oh, it's not letting me. Do I have to put 0? 0 U8? No. So probably it's like U8, U8, U8. Uh-huh. Okay. Okay. So, this is a little bit of a confusion. I don't know why this decision was made. Maybe you guys can explain, but I'm not sure if calling this struct is something I'm happy with. Like, it is a struct at the end of the day, but they want to make it a difference, right? They want to differentiate between structs and tuples. Why did we decide to use the keyword struct for the tuple guy? Like, if you wanted to differentiate them. Right. I guess this is neat, right? Because it kind of works like the C++, right? Like in the C type def, where you just like define the name to correspond to this type. But I don't know. Let me read the Let's see. The Pascal style declaration syntax is easier for the parser, not easier for the human. Wait, when you mean Pascal style, you mean like the one that goes on the left or the right? Maybe, I think you may mean this one is easier for the parser, I imagine, because then it's impossible for you to figure out. Oh, I remember watching a video about this. Ah, you just revived the memory. Yeah, I remember watching a video about this. But I don't remember the exact title. Tuples don't have named fields, well, struct do. W Yaffa, welcome to chat. Yeah, pretty good. Here soon I have to vanish from the face of the internet again to work on organizing billions of lines of information about equation solutions and etc. I didn't work on this yesterday for reasons of needing a break. Alright, Joseph. Farewell. Thank you for hanging around and talking about your project. Penguin Operator is reading GAFA. Program Rust without blue colored hair and sears. Alright, buddy. Pascal style is name type. Oh, I see. I said the same, almost he famous. He the VAP. I said the same, almost he famous. What? Joseph, wait, what do you mean? He the VIP? Who said the same? Oh wait, I'm about to probably learn this to include this language into my project as well. They're not the same and they're used the same language. Okay. I'm not sure what Joseph you mean, but yeah, let me know. Alright, let's see. So I think we solved these errors, right? And then instantiate a regular struct. Okay, let's guess how it's done. I imagine it's done. What's the name? Color regular struct. Color regular struct. And then I just do parentheses. Then I feed into it the values I want. No. Okay. Is it the same as C and C++? No. Is it I specify the type and then the contents? No. Okay. Is it semicolons? Oh, wait, this guy. Mismatch types expected. Found integer. What? Integer? Okay, so it seems like semicolons are only used for the end of expression, so I'm not gonna do that. How does this work? Am I supposed to You? I don't think that's the case because like Rust is supposed to not have. Oh, that scared me for a second. Maybe color regular struct. Oh, should I have to specify them? Do I have to list the struct's contents every time? That's a little annoying, but also better in my opinion, right? It makes the code way more readable. Okay, I'm willing to leave behind this. This seems fine. And then to instantiate a tuple struct, I imagine that it's something like, you know, let green be this guy, and then color tuple struct. And then with parentheses, I specify 0 to 55, 0. Yay! Oh, we still have an error. Unit struct. The fuck? What is a unit struct? Why does this even exist? Why is this guy printing something that's empty? What? Unit struct? What? How does this even make sense? What are you even printing? Wait. Unit structs are fun. Who is this guy? Who is this? Mr. Question Mark? Is it like to get the name of the class it belongs to? Very fun. Who is this guy? Like, okay, I guess we'll figure it out, right? Like, he's very suspicious. It's for debug printing. Ah, okay. So the only use case I can imagine unit structs being an actual thing is to using sort of like enums. Right, where you're like, oh, this guy, right? This guy is like, you know, if this was called something like red instead of unit, right? So maybe I could see it that way, but I don't know. Next. Let's see, structs 2. Structs 2. Okay, so we have some structs here, and then WGAFA is saying, oh, it's very useful. Valley! Welcome back! Yo, we hadn't seen Valley in a while. So debug printing, everything after the colon is a formative declared. Okay, directed Python. Unit structs are for enums, yeah. Okay, that makes sense. So we have a struct order, then a name, a year. Yeah, okay, whatever we have here, main. Oh my god, okay. Whoa. Create your own order using the update syntax and template above. The hell is the update syntax? Huh? Okay, what is... What is the update syntax? Okay, my idea of what an update syntax is, it's gonna be something like this. It's gonna be name, and then I can specify hacker in Rust. And then I can say that this comes from order template. It comes from saying order template dot and then that guy. No. Okay, I give up. Let's take a look at the compiler. So what does it say? If I do order template, hacking is fun. True. So what am I supposed to do? Move occurs because the copy trait value moved here. Oh shoot, I cannot. Wait, what? Yeah, no, I agree, but it's saying that I should use the update syntax. So let's take a look. Oh, sorry. Update syntax in Rust. The struct update syntax. So we get user dot dot and then this guy. I see. So it's like, right, grab whatever you want, and so I just say name hacker in Rust, and then I just do dot dot order template. Expected semicolon. Okay, this is not making sense. What is this guy doing? Oh, I need to include the order, and then this guy, and then use a comma here. Okay, it says, I'm pretty sure it's just struct name to instantiate structs. It's update syntax like struct name with, no, yeah. I vaguely remember this from when I, okay. You sued Rust. Oh my god. Okay. But yeah, okay, so update syntax is this guy. Mismatch types expected string found this guy. What? Does anybody know what's happening? I imagine it's like we have to use string from, but that to me just seems stupid. Why? Why do we need to do so? It seems like it converts this type from the input type. So it grabs a reference to a string. Wait, that's not even a string. That's like a little guy. This is str, which is different from string, right? Why do we have two string types? Who is str and where is their string collection? What? Okay. So I just do string from and then a comma. Interesting. Okay. You should look at your work with nodes side by side. Use to string. Quiz. How many string types exist? If there's more than one, that's already a bad sign in my opinion. Did you read the Rust book? We've been reading it like as we need it. One is a dynamic array of char allocated on the heap. The other is a pointer to a fixed char array that can be anywhere in memory. Well, I am sure gonna love this language. Let's see. The Rust book. Oh my god. I want to code, I don't want to read. I don't want to read. Oh, bro. Okay, let's see. Ownership, we have it, right? References and borrowing in the slice type. Can we find string? Let me find it here, string. Bop. Ba-da-da-bop-bop-bop-bop. Slices. Oh no. Oh no. Brother, you can do it like this without the book, but it'll take longer. Yeah, chapter 4. Okay, slices let you reference a contiguous sequence of elements in a collection. What is a collection? Rust standard library includes a number of very useful data structures called collections. Most other data types represent one specific value, but collections can contain multiple values. Unlike the built-in array and multiple types, the data that these collections point to is stored on the heap, which means the amount of data does not need to be known at compile time and can grow or shrink as the program runs. Each kind of collection has different capabilities and costs, and choosing an appropriate one for your current situation is a skill you'll develop over time. In this chapter, we'll discuss 3 collections that are used very often in Rust programs. A vector allows you to store a variable number of values next to each other. A string, which is a collection of characters. We've mentioned the string type previously, but in this chapter, we'll talk about it in depth. and a hash map allows you to associate a value with a specific key. It's a particular implementation of a more general data structure called a map. To learn more about other kinds of collections provided by the standard library, see the documentation. We'll discuss how to create and update vector, string, and hash maps, as well as what Okay, storing lists of values with vectors. Let's see. Hi. Oh wait, you're using Linux instead of Mac. Yes, MilioDev. Yes, because I moved. You can see the background is different. Right. It's like this is my PC, the one that I have usually at home. I forget that the camera is there and that you guys cannot see. So let me change that right now. Perfect. Store a list of values with vectors. The first collection type we'll look at is vec, also known as vector. Vectors allow you to store more than one value in a single data structure that puts all the values next to each other in memory. Vectors can only store values of the same type. They are useful when you have a list of items, such as the lines of text in a file or the price of... Yes, we know a vector. To create a new empty vector, we call the vecny function, as shown in this here. Okay. Bro, why did you start reading about collections? Bro, because we need to understand. Like, the guy mentioned it's a sequence of elements in a collection. So it's like we need to now know what a collection is. We added a type annotation here because we aren't inserting any values into this vector. Rust doesn't know what kind of elements we intend to store. This is an important point. Vectors are implemented using generics. Yeah, sure, whatever. I do not understand this. What is the need for this guy? Why are we using vec guy? More often you create a vec with initial values and Rust will infer the type of value you want to store. So you rarely need to do this type of annotation. Rust conveniently provides the vec macro, which will create a new vector that holds the values you give it. Why can't we just assign it so that I pass my arguments to the new function? Why are we doing this? Why? This is... Why do we need a macro? Rust doesn't have variadic arguments. It may come from my ignorance, but that's stupid. Like, okay, I'm having an ignorant take over here, okay? But like, I feel that's kind of stupid, no? Like, okay, so there must be a reason why they don't want to have variadic functions in Rust. And that reason may be like, oh, it makes the code difficult to read, it makes it insecure, I don't know, right? Whatever. But you're still allowing for variadic functions, just in a different way. Just with like a syntax that's more unpleasant. So like, what are we doing? Like, if you don't want variadic functions, just don't support it. Just like get rid of it. Say no. Is there a reason why they say functions don't deserve variadic? You know, but we're still gonna allow it just through a different path? Like, what? It seems to me like a weird language design choice. If you're gonna have variadic, make it fit into the language. If you're not, then just don't put it there. I wouldn't say anything if like the macros sort of allowed you to do it in a very weird certain way. But the official library is telling you use a macro for variadic arguments. But like, why? Right? Like, just give me the variadic functions in the first place. The first is Rust seems to always make the worst syntax choices, to be honest. Honestly, it seems like it. Like, I am not liking this like this. But it's okay. It's okay, I suppose. Why is fairies question mark? Oh, this code does not compile. Okay. Yes. Okay. What is the next one? I want to go to string. Storing UTF-encoded text with strings. We talked about strings in chapter 4, but we'll look at them in more depth now. Neurostations commonly get stuck on strings for a combination of 3 reasons. Rust's propensity for exposing possible errors, strings being a more complicated data structure than many programmers give them credit for, and UTF-8. These factors combine in a way that can seem difficult when you're coming from other programming languages. We discuss strings in the context of collections because strings are implemented as a collection of bytes, plus some methods to provide useful functionality where those bytes are interpreted as text. So this is sort of like a Golang type of approach. Okay, in this section we'll talk about the operations on string that every collection type has, such as creating, updating, and reading. Okay, sorry. We'll also discuss the ways in which string is different from the other collections, namely how indexing into a string is complicated by the differences between how people and computers interpret string data. Defining strings. Okay, we'll first define what we mean by the term string. Rust has only one string type in the core. Funny, that's not true. Okay, in the core language, which is the string slice str, that is usually seen in its borrowed form str. In chapter 4, we talked about string slices, which are references to some UTF-8 encoded string data stored elsewhere. I don't think we need to read chapter 4. I think this is understandable what a string is, right? Which is interesting that they first mention chapter 4, then they mention collections. It's okay, as long as it's a kind of reference, so it does not have ownership. Here's a small programming problem. Write a function that takes a string of words separated by spaces and returns the first word it finds in that string. If the function doesn't find a space in the string, the whole string must be one word, so the entire string should be returned. Let's work through how we'd write the signature of this function without using slices to understand the problem that slices would solve. I love this approach. It's very good. So function first word, we accept the string by reference, right? The first word function has a parameter of type and string. We don't need ownership, so this is fine. Okay. But what should we return? We don't really have a way to talk about part of a string. However, we could return the index of the end of the word indicated by a space. Let's try that, as shown here. Because we need to go through the string element by element to check whether a value is a space, we'll convert a string to an array of bytes using the asBytes method. Okay. Next, we create an iterator over the array of bytes using the iter method. We'll discuss iterators in more detail in chapter 13. For now, know that iter is a method that returns each element in a connection, and that enumerate wraps the result of iter and returns each element as part of a tuple instead. Take me back to C, please. The first element of the tuple returned from enumerate is the index, and the second element is a reference to the element. This is a bit more convenient than calculating the index ourselves. Because the enumerate method returns a tuple, we can use patterns to destructure that tuple. We'll be discussing patterns, yeah. Sure, this guy makes sense, yeah, sure. Using s.len. We now have a way to find out the index of the end of the first word in the string. But there's a problem. We're returning usize on its own, but it's only a meaningful member in the context of the string. In other words, because it's a separate value from the string, there's no guarantee that it will still be valid in the future. Consider the program in listing 4.8 that uses the first word function. So we do from hello world, we grab the first word, and then we clear this. This program compiles without any errors and would also do so if we used word after calling s.clear, because word isn't connected to the state of s at all. Word still contains the value 5. We could use that value 5 with the variable s to try and extract the first word out, but this would be a bug because the contents of s has changed. Having to worry about the index in word getting out of sync with the data in s is tedious and error prone. Managing these indices is even more brittle if we write a second word function. Its signature would have to look like this. Yeah, now we're tracking start and ending. Perfect. Luckily, Rust has a solution to this problem. String slices. String slices. So a string slice is a reference to a contiguous sequence of the elements of a string, and it looks like this. Okay. Rather than reference to the entire string, hello is a reference to a portion of the string, specified in the extra 05 bit. We create slices using arranged within square brackets by specifying this. We're starting index is the first position in the slice, and ending index is one more than the last position in the slice. Internally, the slice data structure stores that starting position in the length of the slice, which corresponds to ending index minus sure. So this is just like a slice in any other language. With Rust's .range syntax, if you want to start at index 0, you can drop the value before the two periods. In other words, these are equal. Why? Why? Okay, I don't like this. Like, I understand it's syntactic sugar. I just don't like it. Right? Like, it robs us from like the explicitness that makes it so appealing. Anyways, by the same token, if your index includes the last byte of the string, you can drop the trailing number. That means these are equal. Same thing. Same thing. I understand this is more convenient because you may not know, right? Writing s.line all the time is annoying, but I feel I would like this. Okay. With all this information in mind, let's rewrite first word to return a slice. The type that signifies string slice is written as &str. Okay. Good. And so, okay. Okay, that's fine. Much harder to mess up because the compiler will ensure that the references into the string remain valid. Because I imagine the compiler just checks, oh, never mind, there is a reference that's still alive, right? And that is word. It's alive here. So that makes sense. Sure, strings literals as slices. Recall that we talked about string literals being stored inside the binary. Now that we know about slices, oh, I did not know this. Interesting. So string literals are stored inside the binary, right? You listen to Nerdcore? What is Nerdcore? We're taking a break. Give me a second. Music, I imagine, is a genre defined by its lyrical focus on geek and nerd culture, such as video games, anime, comic books, science fiction, and technology. When it began primarily as a subgenre of hip-hop, it now spans pop-punk, electronic, and rock, driven by a strong DIY, self-published online ethic. I have no idea what this is. Who is the biggest nerdcore artist? I have no idea what this is. In the English-speaking market, prominent heavyweights. Who are these people? Interesting. I'll have to take a look. I'm not sure if it is for me. We'll see. But this is strange. What is nerdcore? Seems like it's just lyrics. Interesting. There's always a something for everyone. Oh, you guys couldn't see. Oh my god. Oh wait, never mind. It's because I had the menu open. There you go. Yay. You provide me cracker more. Yes, it's all I listen to, but specific artists only. I see. Yeah, I mostly listen to like... Yeah, specific artists, but maybe not of nerdcore because I don't know what it is. I listen to rock and to. I listen to specific artists. My favorite artist is like Cage the Elephant, and then I like Aurora Axness. I've listened to her for like a while. It's like tranquil music in a sense. She's transitioned to like electronic music and a bunch of stuff with tomorrow. But yeah, there's a French artist called Pomme. I like Pomme too. Very tranquil music. And Hosier, I also like Hosier a lot. And Milky Chance. That's my list. Cage the Elephant, Aurora, Pomme, Hosier, and Milky Chance. And that's basically the music I listen to. And yeah, we'll have to see what nerdcore is. We'll have to take a look at it. But yeah, let's see. What is this? What is this, bro? Oh yeah, here. String literals and slices. Nerdcore isn't as mainstream, which is nice when others finally learn about it existing. Yeah. Yeah, I'll have to see it. I'll listen to it after. Let's do it! Okay. Let's see. Recall that we talked about string literals being stored inside the binary. Now that we know about slices, we can properly understand string literals. The type of S here is $str. It's a slice pointing to that specific point of the binary. This is also why string literals are immutable. This is an immutable reference. String slices as parameters. Knowing that you can take slices of literals and string values lead us to one more improvement on the first word, and that's its signature. A more experienced rustacean would write the signature shown instead because it allows us to use the same function in both string and str values. If we have a string slice, we can pass that directly. If we have a string, we can pass a slice of the string or a reference to the string. This flexibility takes advantage of deref coercions, a feature we will cover in the... Okay. Defining a function to take a string slice instead of a reference to a string makes our API more general and useful without losing any functionality. Okay. Okay, other slices. String slices, as you might imagine, are specific to strings, but there's a more general slice types too. Consider this array. Just as we might want to refer to part of a string, we might want to refer to part of an array. Yeah, that makes sense. This slice has the type this guy. It works the same way as string slices do, by storing a reference to the first element and a length. Use this kind of slice. Yeah, that makes sense. Okay. And so here, where we were talking about collections, okay. We also use the function from to create a string from a string literal. The code in this listing is equivalent to the code. Yes, okay. So toString we can also use. Because strings are used for so many things, we can use many different KPIs for strings, providing us with a lot of options. Some of them can seem redundant, but they all have their place. In this case, string from and toString do the same thing. So which one you choose is a matter of style and readability. Don't know if I like that. Remember that strings are UTF encoded, so we can include any properly encoded data in them, as shown in this listing. Yay! Okay. Updating a string. A string can grow in size and its contents can change, just like the contents of a vector. If you push more data into it, in addition, you can conveniently use the plus operator of the format macro to concatenate string values. What? Push str, okay. Through these two lines, S will contain foobar. Oh, what? Push str method takes a string slice. What? Oh, yeah. I thought that, yeah. And I was like, wait, there's no way. It has to be mutable because it's mutating it. Yeah. It pushes here. Yeah. The push method takes a single character. Yeah. Plus, okay. Yes, okay. Yes. In the standard library, you'll see add, define, use, and generics and associated types. Okay. Sure. Indexing into strings. Yeah, this is one of the things I'm worried about, right? Because if you're using UTF-8, it would be like, oh, I want to enter sort of the first character, right? And it would give you like maybe this guy, but that's like not a single character, right? Like that's, yeah, I find that like, how are they gonna solve this? Because if a string is just, you know, a collection of bytes, then does position 0 return the first byte or the first UTF-8 character? It's not very clear to me. And this is why you should never do this with your strings. Okay. Let's see. Here. In many other programming languages, accessing individual characters in a string by referencing them by index is a valid and common operation. However, if you try to access parts of a string using indexing syntax in Rust, you get an error. Okay. The error tells the story. Rust strings don't support indexing? Oh no. A string is a wrapper over a vec U8. Let's look at some of our properly encoded UTF-8 example strings from listing this versus this one. In this case, len will be 4, which means the vector storing the string all is 4 bytes long. Each of these letters takes 1 byte. Okay, yeah, this is the problem we're looking at. If you were asked how long the string is, you might say 12. In fact, Rust's answer is 24. That's the number of bytes it takes to encode this in UTF-8. Yeah. An index into the string's bytes will not always correlate to a valid Unicode scalar value. To demonstrate, consider this invalid Rust code. You already know that answer will not be 3, the first letter. When encoded in UTF-8, the first byte of 3 is 208, and the second is 151. Oh, sorry, that's not a 3, that's the Russian letter. Okay, sorry. So it would seem that answer should in fact be 208, but 208 is not a valid character on its own. Return a 208 is likely not what a user would want if they asked us for the first letter of the string. However, that's the only data that Rust has a byte index 0. Users generally don't want the byte value returned, even if the string contains only Latin letters. Okay. The answer then is that to avoid returning an unexpected value and causing bugs that might not be discovered immediately, Rust doesn't compile this code at all and prevents misunderstandings early in the development process. Another point about UTF-8 is that there are actually 3 relevant ways to look at strings from Rust's perspective: as bytes, scalar values, and grapheme clusters. If we look at the Hindi word, this word, written in Devanagari script, it is stored as a vector of U8 values that looks like this. That's 18 bytes, and this is how computers ultimately store this data. If we look at them as Unicode scalar values, which are what Rust's char type is, those bytes look like this. There's 6 char values here, but the 4th and 6th are not letters. They're diacritics that don't make sense on their own. Finally, if we look at them as grapheme clusters, we get what a person would call the 4 letters that make up the Hindi word. Oh no. Okay, I kind of see the appeal. At the same time, I think this is overcomplicating the issue. I feel like prefer the simpler approach where it's just a string is just a sequence of bytes, and you should just, you know, be able to index and find bytes inside it. I found a reason Rust doesn't allow us to insert into a string to get a character is that indexing operations are expected to always stay constant time, but it is impossible to guarantee that performance with a string because Rust would have to walk through the contents from the beginning to the index to determine how many valid characters there are. Interesting. I feel that's a better reason. But you generated the problem. you yourself put yourself into. So I don't know. What would be the point of a string that's just a sequence of bytes? You have vec u8 for that. Yeah, in Rust, what I'm saying, it's like, I prefer the C approach, where they're like, there's really not a string type, you just have a sequence of bytes, and that's it, right? If you need more sort of mechanisms to deal with like UTF-8 and everything, then you have like a proper library for it. But you don't have to include that into your program. It's not like overhead or anything like that. I feel it makes things simpler. Because like, if you really stop to think about it, at least personally, the amount of times I've had to worry about UTF-8 and including like actually readable characters is 0. Well, it's actually 1. But like, compared to the total amount of programs that you generate and all of the things you need, like, it seems to be rather unnecessary and it makes it more complicated. I see the appeal though. So it's like, I don't know. I strongly disagree. Strings and UTF-8 are so common that it would be insane not to have them built into a language. Well, I mean, you have C, you have C++, you have like all of these guys that like survive completely without it. I do see the appeal. I guess like strings are very common, and they're used in applications, right? It's just like, like in the context of Rust, for example, being like a systems programming language, I don't see it worrying a lot about things like these, right? Where you're like, oh, I need to represent all the characters well, etc. Right? Like, I think you're rarely going to use that when it comes to systems programming. It's like, it is convenient, but I feel it just makes it a little bit more complicated. Although I guess it's a good reasoning to say, well, you can just use vec u8, right? And you just have the option of string as something you can play with, right? And if you just want to ignore the whole string thing, you can just use vec u8. So I don't know. It's necessary complexity, in my opinion. I'm not sure if it's necessary. That's the thing. Because like, you can also just use as bytes. Yeah. So I guess, sure, it's like a good middle ground. Maybe I'm biased by C, right? The fact that like, it doesn't have it, and I think C has a very simple model, and it allows you to think very straightforward about it. Yeah. But anyways, and all of this we already know. Okay, now we go back to our exercise. let me transport this here. 1.3, perfect. Great. Vast majority of the world needs non-ASCII characters. Yes, I agree. I'm saying like, for a systems programming type of language, like, is it something we really worry about? I'm not sure. But it is a good argument, right? That like, supporting non-ASCII out of the box is, I'm willing to be on the fence about it, to be like, okay, yeah, I see it. I see the benefits. But yeah. Okay, so this simple thing is what led us to all of that. So great. Let's see. Structs 2, then structs 3. Also, one question. Does it mean that if strings are stored in the binary, like string literals are stored in the binary, does it mean that they have a sort of, like program-wide scope, which means like I can just create a reference to this guy and just use it all the way through my program? I imagine yes, right? Like that seems to make sense to me. We'll see later. Let's see. Struct package. Okay, structs contain data, but can also have logic. In this case, in this exercise, we have defined the package struct. I think it's still just lexical scope. Okay. I see. We have defined the package struct. You want to test some logic attached to it. Okay, so we define the package struct. Sender, country, recipient, country, weight in grams. Ooh, interesting. Implementation package. So this is the way you add methods to structs. I feel I kind of like this. Right? It's like a good way to separate it, where you have struct refers to the data, and then you add the functions later somewhere else. Pretty good. Sender country, recipient country, weight in grams, self that. This isn't how you should handle errors in Rust, but we will learn about error handling later. Okay. Then we return what? Self, sender, country, recipient. Okay. Is international, so read the tests that use this method to find out when a package is considered international. Okay. To do, add the correct return type of the function. Okay, so we just gotta complete this. So the text say, assert that this is international, and the sender country is Spain, and the recipient country is Russia. Local package. Okay. So whenever the two guys are the same, then it's not international. Okay, so let's implement that. Here is international. Let's see. So how would we do this? So imagine that we say return self dot. Yeah. So sender country. Can I just use double equals in here? Something tells me no, but self dot recipient country. Okay. Do I have to specify this returns a bool? Oh, okay. Comparison between two strings is great. Yay. Add the correct return to the function signature. So this guy should return get fees. So cents per gram, it's VU32, so I imagine we return a U32. And to calculate the package fees, we just look at the text, at the tests, which say, let's see, cents per gram, package. Oh, okay, yeah, no, never mind. It's just easy, right? We return self dot weight or something like that. Yeah, weight in grams times cents per gram. Oh, sorry, times cents. Yay! Perfect. I think we solved it. No? Oh. Failure. Tests your order. What? Oh, structs 2? Oh wait, we didn't pass this? Why? Panicked at exercises, assertion left is equal to right. What does that even mean? If I change the file, will it refresh? No. Okay, what's happening? Tests your order. Panicked at line 48. Oh, because, okay. Apparently we need to also update count. Yay! Next, and then that guy we should pass. Oh no, okay. Is international, this should actually be different. Yay! Okay, perfect, we passed. Next. Now we can transition to enums. Enums. Oh my god, what are enums? Okay. Define a few types of messages as used below. So probably resize, move, echo, change color, and quit. Okay. So can I include a semicolon here? Okay, I see. Sure, yeah, keys are enough. That's great. Let's go to next. enums 2. Define the different variants used below. Oh, what? Enums with parameters. That's cool. Okay, first the great decision from the Rust. Okay. No variant name resize found for enum message. So do I just implement in that way where I say, let's see, resize, and then I say width is a U32, height is a U32. Ooh, that's interesting. So then I do move, and move seems to be, oh. Why is it using parentheses? Question mark. Okay, move, and I just imagine that you pass through the point. Aha, perfect. The next one is echo, then change color. So echo, then you need to pass me a string and change color. Then you need to pass me a tuple of U8, 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 U8. I feel like another Rust W is the fact that they include sort of the amount of bits inside the thing itself. I feel that's pretty cool. Yay, inside the name. Finally, we need to include quick. Will it compile? Yay! Okay, next. Enums 3. Oh, there's no errors. Oh, never mind. So it says test failed. Okay, create a match expression to process the different message. A match expression. Is this like in OCaml? Is this like in OCaml where we are able to decompose? If so, this is very cool. Yeah, so message, right? So I imagine it would be something like match and then message. Then we include, oh. Yeah, and then I include message and then resize. I pass width and height, and then I do like color or something like that. Or like these guys. Oh shoot, what am I supposed to do? Wait. Match Rust. Match Rust by example. Rust provides pattern matching via the match keyword, which can be used like a C switch. The first match in ARM is evaluated and all possible values must be covered. Oh, so it's like a little arrow. My favorite thing is that the LSP can autofill all the missing branches of a match. Yeah, since it has to be exhaustive. Wait, that's pretty cool. That's very, very good. W Rust decision. I love this. I love this. So the match expression works exactly like in OCaml because you need to return it, right? I imagine that this arrow, like the match expression just collapses to a value. Is that the case? Right? Something like that? Maybe. Let's see, resize, and then you pass me width and height, so then I imagine, well, no, actually, no. No, because here they're just asking me to do a bunch of stuff, so never mind. So what if I want to include like imperatives to like, what am I, yeah, all the branches must return a value of the same type. Okay, so it's the same as OCaml. I see. The thing is like, that means I cannot do self dot height equals height, right? Like, this would be prohibited. Yeah. So what am I supposed to do? Am I supposed to make this something like self equals this, and then say, okay, I'm confused on this one, because it would be way easier if it just worked like a switch statement. instead of requiring me to be sort of the OCaml type of way. How does it know all the branches it can be? Because you just declared it over here. Yay. But, so how am I supposed to do this? Message resize. Width height, right? You can have multiple statements inside the arm if you use brackets. Oh, really? Oh, wait, that's great. So now I just do this and stuff that width. And width. Yay! And so I assume now that the value that we need to return is just the unit value, right? The nothing value, the parentheses value. Okay, that's great. And so let me take a look at the syntax again. I separate them with commas. Okay, that's perfect. Wait, this is very good. This is very pretty. I love this. Message resize, and then I do move. Okay, move. Move, and then we move to this point, and then I need to sort of attach what's the thing I'm talking about. And I'm gonna call him P. I imagine there's no need to specify the type of this guy, right? Oh, sorry, the name is not move, it's message move. Message move. Yeah, I don't need to specify the type of T because it deduces it. And then to move from one point to the other, where's the point thing? X and Y, okay, and then position. Okay, so imagine I just do self.position is equal to P. Perfect. Then comma. I mentioned that the destructuring of these guys when they are used in the match expression consumes the value. That is like the value is moved and I cannot use message again. I feel that that is like what would make sense according to what we've been seeing. But yeah. Okay, move. Then echo. Let's echo something. Let's call it here string. String. And then self.echo. And I just do, oh sorry, this guy should be a string. Okay, it's inconvenient that I cannot call it str. Can I? Actually, well, the compiler may be able to notice that this is not a type. Oh, that's pretty cool. Let's go str, then message, echo move resize change color. And so this would be red, green, blue. Then I can just do this. Self dot change color and then RGB. Wait, did I have these methods available all the time? Like change position? Oh yeah, okay, move position. I'm just gonna use that. Okay, perfect. Yay! Alright. So I imagine just like self dot resize. Yeah, width and height. Perfect. Non-existent patterns, of course we quit. Width. Okay, and then what do I do? Self.quit. Oh, perfect. Yo! Perfect. Wait, this is a very cool part of Rust. Really liked the match expression. Alright, I think we could keep learning Rust. I think I'm gonna take a break. Let's take a small break, okay? And yeah, so currently it's 3:30 p.m. Let's take a break until 4. And At 4, we'll continue either learning Rust or doing something else. But yeah, let's take a break. All right. I'll see you guys soon at 4:30 p.m. Eastern time. So 30 minutes from now. I think I'm just gonna include that into the timer, right? So 30 minutes. Um, yeah, I feel that's reasonable, right? So yeah, we'll see you guys. I gotta eat. I gotta, do other stuff. And 30-minute break is reasonable. We'll come back and continue with this. Continue learning. So 3 times. Yeah. All right. 1800 seconds. I'm just gonna create the countdown, right? And let's see. Yes, perfect. Okay, that sounds good. All right, I'll see you guys in 30 minutes. Whee! Hello! Hello, everybody. Welcome back. The stream is started again. Sorry I had to take a few more minutes because I was eating. Yeah. So, yeah. Welcome back, guys. Hopefully everyone is fine. Hope that's the case. And, yeah. So, today, we're learning Rust right now. And hi, Andrew. Hello. But yeah, so welcome everybody. And transition here to the thank you now. But yeah, so I think we're currently learning Rust, right? And one of the ways of learning Rust would be going through all of the rustlings examples and reading the Rust book. It's gonna take like quite a while, and it sometimes gets a little bit boring. I think something that I was thinking during the break is hi go to cheeseburgers. Hello. So something I was thinking during the break is the fact that I'm still in college, right? Which means I really need to prepare for a job. So one thing that I feel would be productive to do is to try and solve lead code problems using Rust. I don't know the totality of Rust, but that means like I at least have a problem to apply the knowledge to, and like it is a little bit more entertaining to code something that seems to have a purpose rather than just solving the rustlings exercises. If we ever get confused at some point in time, we just go to the Rust book and take a look at it and try and understand what's happening. We're not going to get rid of the rustlings exercises. We're just going to have it as a complement too, right? We just do these two things, sort of at the, we exchange the two when we get bored of one. So yeah, hopefully that's gonna be entertaining. We'll try it out. Welcome to the coding scene, and welcome to the beautiful world of Linux. Yeah, so I think one good thing to do, we can just enter lead code. Right, I think I'm checked in. Then inside of problems. I think one thing we can do is use lead codes 150. Which I've been doing in C++ actually, because many interviews require C++, but we can just apply this, but to Rust, right? I feel it's it's a good thing. It's a good thing we could do. Yeah. What do you guys think? Give me a second. It's very hot in here, so I'm feeling kind of sick. But it's okay. There are a lot of lead coders on Twitch. That's true. But, it feels to me that it has a little bit more purpose, or at least I find it more fun to learn Rust this way, rather than just doing rustlings. I feel doing both rustlings and lead code helps. And once again, like it is helpful for me too, given that like I'll have to face interviews soon. It's not that my favorite part, but it is something that that has to be done. Yeah. So, are there any? Maybe there is some sort of library. Let's see. I want to solve lead code parts because those are entertaining. Those are very entertaining. I think we can filter. Let's see. Status is not completed, and the difficulty is high. Perfect. Okay. It's got it. Okay, give me give me guys a second. I think I have to go. Like, I'm feeling I'm feeling weirdly sick. I'll be back in like a few minutes while I don't know, it's really hot in here. But yeah, I'll be back and then I'll turn on stream when I'm back, okay? Alright, see you.